both in Tel Aviv and Jerusalem, that has been fully committed to the sciences of economics, and maybe that's the way to contribute to society more rather than to do other things. So let me wish Yoram Mazar Tov and success for the rest of his career. So in the present program, we're going to have two talks. One of them is by Robert Willis, estimating 90 uncertainty from survival probability question on the HRS.
I'll tell you what that's the health and retirement. Okay, I'm very pleased to be here, and Yoram and I have been first got acquainted a frighteningly long time ago in about 1970. We got acquainted and well acquainted, and our families got well acquainted in the late 70s, and then I invited Yoram to spend a year at Stony Brook, where I was at the time, and he and his family came, and we started some work that was on issues of child support, and basically came to a model in which fathers didn't spend very much on their children. It was kind of a theoretical explanation for what in the United States is called deadbeat dads. Another pioneering person in the field of economics of the family is Ted Bergstrom. And last night in my email, I discovered a message from Ted that suggested another topic that should be in a book that's forthcoming, I believe, momentarily, I gather not, by Browning, Chiapori, and Weiss. And here's this is on mothers may not be the best parents either. So there'll be a new chapter in the book on bad parenting. Let's see if I can. Okay. Oops, I didn't want that guy to show up here. Let me just go back into the. Let's see. Can I want to start here. So. Okay. So this paper is estimating 90 uncertainty from survival probability questions on the HRS. The HRS is the Health and Retirement Study. It's a study of about 20,000 older Americans that's longitudinal and has been going on since 1992. And it pioneered the use in kind of a large-scale way of asking subjective expectations questions, essentially along in a numerical format. And as I'll show you, it's a format that says sort of on a scale of 0 to 100, how likely is tomorrow to be a sunny day? How likely is that you're going to survive to age 75? How likely is it that the stock market's going to go up? And a variety of kinds of questions. The format of these questions was proposed initially by Tom Juster and really analyzed by and advocated by Chuck Mansky, who's got a really very nice and thorough discussion of these subjective probability elicitations in his Fisher-Schultz lecture that just came out in Econometrica, and Chuck and I and Michael Hurd, who's made a lot of use of these data, have a sort of larger scale research project, which is going to really try to understand sort of what can go on in terms of making use of these, understanding these elicited subjective probabilities and making use of them in a variety of models. And let me just go to, since I've got a lot of slides, I'll try to move. I can't use that. How do I move one slide at a time here? Just the down arrow will do it. There. Okay. Okay. So the opening point in this paper is really to distinguish between risk and uncertainty. Since Frank Knight introduced the distinction, economists have recognized that risk is a special case of uncertainty in which probabilities are known. And sort of if all the probabilities are known, then we sort of have mathematical procedures to deal with them. We can certainly incorporate them in models. But Knight suggested that it's really a minority of situations in which risk is really known. It could be like gambling devices where they're explicitly engineered so that you know what the probability is. Or they could be cases where you've got large amounts of data, like actuarial data, where you could form good frequentist estimates of risk. But in many areas, the problems that confront entrepreneurs, which is what he was interested in, you don't know what, you know that your returns from an investment are going to be uncertain, but you don't know really what they might be. You don't know you don't really know the probabilities. And Knight sort of suggested that economics was equipped to deal with issues of risk, but it was not really well equipped to deal with issues of uncertainty in this more generalized sense. And I think the treatment of uncertainty, for the most part, languished in economics until after the Second World War, and then it kind of came back in when kind of ideas of subjective probabilities and personal probabilities, that sort of thing, was introduced by Savage and others, in which people were assumed to have probability beliefs, and those beliefs could cover everything from things that involve gambling devices and cases where there's lots of objective evidence to other cases in which there's no evidence at all. And so what I want to do is I want to sort of emphasize this. And I want to, what I really want to do is I want to sort of, the point of this paper is going to be primarily to sort of say what's the mapping between these subjective beliefs that people may have in the sort of post-Second World War kind of theory to the kinds of answers that we get to subjective probability questions. And so that's kind of, and I'm going to first talk a little bit about these subjective probability questions, a little bit about the HRS and some other surveys just to get you familiar with the area, and then I'll kind of develop a theory and estimate it. The ultimate goal of the theory will be to try to sort of retrieve something about what the distribution of beliefs about, in this case, survival probabilities will be. So let me just begin, and I'll try to kind of move quickly through these slides. The HRS asks a bunch of different kinds of probability questions and they ask things about what's the probability of a sunny day, what's the probability that you'll be working at age 62 or age 65. They ask about the probability of survival to a given age. They ask about changes in Social Security policy, stock market returns, and a variety of things of this sort. Notice that all of these questions are forward-looking, and that's kind of why, fundamentally, why I think economists would be interested in them, because all economic models essentially are forward-looking, and yet we often don't have any data on that crucial part of the model. So I think I already mentioned these. I'm having the same problem that Bob had about not knowing what the next slide is going to say, so I think I already mentioned these, and I'll just go on. And I also mentioned the broader project, and I want to just talk about it quickly. I think I got this a little bit out of order in my slides. So this paper is going to be about the determinants of these beliefs. Accuracy of beliefs is another topic. Change in beliefs is what determines changes, what causes you to change your probability beliefs, and then how do beliefs affect behavior. All of those are things. So the HRS survival probability question, which is the one that we'll be concentrating on in this paper, says, using a number from 0 to 100, what do you think are the chances that you'll live to be at least age X? And the sample consists of people who range in age from about 50 to over 100. And people over 90 are not asked this question, but everybody 90 years of age and under is asked the question, and they're asked to a target. So for people who are between 50 and 70 years of age, they're asked to age 80, and then it increases by increments, so the time horizon is always about between 10 and 15 years away. Okay. I don't know. This seemed to have got mixed up. So the two key findings from previous research results using the HRS subjective probability questions are kind of two things that, on average, these probabilities make sense, and that actually seemed to be to encourage a lot of people to feel that this would be worthwhile doing. Michael Hurd and Kathleen McGarry first looked at these, and they found that the survival probabilities conform to life tables. Bequest probabilities behave sensibly. Retirement can be analyzed using expectational data, and there's sort of been a variety of things. But something has been noticed by a variety of people, I think perhaps most persistently by by a paper Michael Hurd, Dan McFadden, and Lee Gann on this. Noticed that there are a lot of individual probabilities that are very noisy, and they have a lot of heaping on focal values. So people are asked a question, say about survival probability, and some of them will say, well, my chance of surviving to 15 years from now is 65% or something like that. But a very large number of them will say, give answers like 50% or 100% or 0%, and those seem a bit troublesome. So here's these kinds are illustrated by the data that I'll be using actually in today's talk. So here's the kind of histogram of the answers that you get for 3 different age groups. For 50 to 64-year-olds, 65 to 74-year-olds, 75 to 90-year-olds. And you can see that there's a lot of heterogeneity in those expectations. So they run from left to right, all the way from 0 to 100. There's also very notable heaping, particularly at the 50. And so forth. So, but if you sort of average them, you can sort of say, look at the 50 to 64-year-olds, the subjective mean is 66%, the life table's 59%. For 65 to 74-year-olds, the subjective mean is 57, the life table's 58. And only when you get to the older ones, 75 to 90, there seemed to emerge a fair discrepancy where the subjective mean is quite a lot larger than the life table expectation. As we speak, actually, there's an extension of the health and retirement study that is covering a large number of countries in Europe, I think about 11. And they're having a first results conference, and I just pulled this off, the first results from that. And yesterday I attended a meeting with Yoram, actually, that announced plans for Israel to join the share. So in that sense, there'll be comparable data to the HRS being collected in a very large number of countries. And this is sort of the pattern that you get from the European countries. And you see roughly the same pattern I just showed you in terms of the means and the life table values seeming to line up pretty well until you get to the older ages, where they start notably, all are notably higher for the oldest people than for the younger. Here's an example of sort of these lining up, and this is sort of, these are relative odds for smokers versus non-smokers, and there are a lot of covariations that have been shown. That there's actually a book using the HRS data on expectations and trying to understand smoking behavior and how that's used. It's a book with Frank Sloan and others called The Smoking Puzzle in Harvard University Press. Here's another example of something with a predictive power that is a histogram where on the bottom is sort of what was the answers to the question in 1992, and on the top is the odds ratio of for survival in 10 years in the 10 years later in the HRS, which is a longitudinal study. And you can see there's quite strong relationship for probabilities between 10 and 50, really quite strongly declining, and then not much relationship for higher, suggesting that the people, somebody who says my chance was 70% and somebody who said my chance was 90% or 100% didn't have much different information to be going on, perhaps. Here's sort of a bunch of other events, and I'm not going to dwell on this, but it just shows that this heaping tendency, these giving focal answers, is not confined to the survival questions. It's a quite common phenomenon across the different different things, and this is different types of questions. I won't dwell on that. And so from now on, I'm going to be trying to talk about, well, you've sort of seen what these answers to these questions sort of look like. The question is sort of how are those answers related back to sort of people's subjective probability beliefs. That's sort of the goal of what I'm going to be talking about. We are beginning with this assumption that many people may feel ambiguity about the true probability of an event, but they have some sense about which possible probabilities are most likely. And we imagine their beliefs take the form of a prior distribution of probabilities. And given these beliefs, we develop and test a theory about how people respond to subjective probability questions that are posed in the HRS. So here's an example, and it's just to give you an idea what I'm thinking about. In the bottom chart here, you could think of a gambling device, like an urn that contains 50 white balls and 50 black, or a coin or something like that. The belief is that the probability is 1/2. If we add some uncertainty, that starts to spread the distribution a bit, and the second one up would sort of be that, well, the probability is somewhere between 40 and 60%. Next one up, it says, well, it could be anything between 0 and 100. So it's a uniform probability. And the final one says that, gee, you know, it is kind of a U-shaped thing, and it's actually the modes of this distribution sort of are heading off towards 0, and it has two modes at 0 and 100, and not much mass in between. These are sort of different, and I'm going to be characterizing these as different levels of belief, and indeed I'm going to be arguing that these would be represent increases in uncertainty in the same sense that well, let me not make that argument, but sort of that they're in another paper, and I think I'll not go in that direction right now, but you can sort of argue that that movements up through these graphs represent sort of will result in mean preserving spreads of the probability distribution, and can be thought of as increasing uncertainty in the same sense that the standard Rothschild-Stiglitz mean preserving spread in risk represents an increase in risk. If we move away from probability 0.3 kinds of, or probability 0.5 kinds of things, you can get to probability 0.3, and here we see again sort of what happens is that this thing starts spreading. It sort of ultimately starts to become J-shaped in the middle, and it goes up and becomes U-shaped. And I'll show later in a moment where those things came from. And so the question is, what do they answer? And one possible answer that I think economists would really like to be is, suppose that your beliefs are represented by this function G of P. So if my beliefs are this, I say that the mean of that function, the probabilities could be anywhere between 0 and 100, but they're sort of concentrated at somewhat larger values, and the mean of that distribution is 2/3, 0.67. And it would be nice if people would give that answer, and indeed that's the kind of answer that I think most economic models think that people are giving. That is, whatever ambivalence they have in their head, they resolve in their head, and they then pop out with an expected value. But this is a cognitively very difficult calculation. Now, the probability questions that I showed you are questions. We have a whole series of them, and we cover a lot of other topics in the HRS, and people take about 15 seconds to answer these questions. So, sort of thinking, well, do they really do this integration? You know, think of what are all the probabilities, weight them by how likely they think a given probability would be, then do multiplications and summations. That seems very hard. This response, but uncertainty doesn't really matter in conventional SEU theory, you know, so because probabilities interlinearly, but there are other models in which uncertainty does matter. They're in sort of non-expected utility models with ambiguity. It matters in sort of situations of repeated risk. I've got another paper with Lillard that shows that uncertainty matters, but that's not sort of where I'm going. Okay, so the modal response, so the alternative hypothesis that I'm going to sort of argue or use in this paper is what I call the modal response hypothesis. When asked to give a single number between 0 and 100, assume the person gives the most likely probability among all possible probabilities and does so in 15 seconds. The mode's cognitively less burdensome, and it's actually a very good estimate of the mean if uncertainty is low. And the modal response may be what a psychologist like Gigerenzer and his colleagues have called the fast and frugal algorithm. That is, the brain is trying to figure out how to make these calculations, and this may be a sort of reasonable approximation approach. If the mode is the most likely probability, then you'd get an exact, what we can call here an exact answer if there's a single mode. So if there's a mode at point 8, as there was in the picture I showed you, this theory would say the person would answer 80. If answer is 0 or 100, if the largest mode is at 0 or 1, and in that case, we'd expect an answer, okay, that's obvious. And then finally, 50 if you can't determine which is the largest mode. So 50 then represents a case where uncertainty is really quite high and is basically, I think, or at least roughly the same kind of idea that psychologists Bischoff and Brun de Bruin have argued, have given the label epistemic uncertainty, and that many people in survey situations have gotten an answer to a question, say the respondent answers, God only knows. And so there's now a model of beliefs. Okay, that came out clear enough. So let me just, this is sort of all the equations of the model, and I just want to give you some intuition for what I'm doing, and then I'm mostly going to do with pictures. So the basic question is that I want to have sort of a model that allows people to hold beliefs, and the beliefs that they hold have sort of some kind of central tendency to them and some kind of spread to them. A flexible model for this purpose is what we could think of as kind of a heterogeneous probit model. So suppose there are two parameters involved. One is mu, which will represent sort of the level of risk, and the other is delta, which is a parameter that's going to represent the sort of degree of uncertainty. And so if we said, well, what is the probability? Well, the probability, and I'm going to be operating kind of within a probit framework in the sense that I'm going to have an index here which says what's the probability that the index is greater than 0 given for any given value of mu and delta. Well, if we just carry that over, what you get is in line 1 is a standard probit equation that says that phi, the probability, is equal to mu, which is sort of what the risk stuff, so it might be like my age and my sex and my race in a survival curve, and delta, which is sort of reflects sort of my degree of uncertainty. Now, you could think of like a representative actuary who's been working in this stuff all the time, and he doesn't have anything distinguishing him from any other person of his sex, race, and age, and he could say, well, I can go look at the data and I can estimate this thing with a great deal of precision. In that case, delta for him might be really quite low. But now suppose that there's some things that, he's noticed he's got some breathing difficulties and can't climb steps as well as he once could, and has some rashes breaking out and various other infirmities that start creeping along. And he could ask himself, well, how well do these, what are my risks? Well, I now don't have any really objective data that sort of come to people that are exactly like me, and that might induce some spread. And so we're thinking that, I'm thinking of delta, the things could be benign, in which case delta could be thought of as like a positive number, or the things could be bad, in which we could think of delta being a negative number, and so variations in delta will then induce a distribution. Working this through, the algebra of this will result in this down by line 5 is the subjective distribution of beliefs that can be derived from that model. And it's just a in a lot of ways, the way you should think about this is a kind of flexible functional form that will allow us to obey the rule that probabilities all have to lie between 0 and 1, and that will allow us to introduce covariates that will, some of which will influence mu and some of which will influence delta. And I'll show you pictures of that. And then some other, the next lines are that, that the formula for the mode in this distribution is phi of mu divided by 1 minus sigma squared delta. And that's will turn out to be an important thing, because the mode, if sigma delta is equal to 0, so that you have exact information, then the mode, the mean, and the median are all the same. And as you, if mu is not 0, if mu is 0, then everything is 0.5. But if mu is bigger than 0, let's say, then as sigma squared grows, it tends to drive the mode toward 1, and we'll see that'll play a role. And then here's just the parameterization where we put in these z's. The individual is assumed to have access to a whole information set reflecting z star p, which is information about the risk part of this. This z star a, which is the information he has about the uncertainty part. And then we only observe a subset of the things that he observes, and so there's some observable z's and some error terms that are jointly normal. So this is sort of what the various formulas are. This is what, if you draw this picture, this is what the thing. So here's a picture that says, well, here's kind of illustrates what kind of beliefs you could have depending on sort of risk and uncertainty. So along the horizontal axis, we're moving from 0 to 1, and you could notice that f or phi, I guess this should be the evaluating the standard normal distribution at x beta or at mu is essentially the median of these distributions, since this delta thing is assumed to be normally distributed. So it's always symmetric around that. So half of the cases will be above and half below. And what you sort of notice in this picture is there's sort of a pattern. And if we follow this modal choice hypothesis idea, the notion would be if you're in this area, all this area that's marked exact, you see the subjective distributions are unimodal curves. And so the most likely probability is some number that I'll characterize an exact number. That's like the 80 or the 65 or the 30 or 31.3 for that matter. If we go up to this upper level, we see a bunch of these U-shaped, inverted U-shaped curves, and they have two arms, and there we say that people are so confused that they suffer from epistemic uncertainty, and they give 50s for answers. The left side is where things go to 0, where there is a mode, but the mode is at 0, or the other direction at 100. So that gives us a pattern, and so when I first discovered this pattern, I wanted to sort of see, is there any validation for this? And I'll just show you. It's hard to validate because you could measure sort of a lot of the things having to do with risk, but the uncertainty is hard to get at. And many of the things, like with survival probabilities that affect risk, you'd expect also affect uncertainty, so there'd be kind of an identification issue here. And but one idea that we had was to sort of say, well, suppose that we have this question that's been asked in the HRS, which is about a sunny day. What's the probability, on a scale of 0 to 100, what's the probability tomorrow will be a sunny day? And we administer the health and retirement study, very large study, 20,000 people, all over the country. So we administer it in Phoenix, and we administer it in Ann Arbor, and so forth. And we have a field period that lasts most of the year. So we have some of the surveys are taken in February, and some of them are taken in July, and so forth. So we have a lot of variation in the circumstances of what tomorrow is going to look like. So I decided to take, well, suppose we formed cells containing people who are all in the same month and same location, everybody in Ann Arbor in February, for example, and ask them what's the probability tomorrow is going to be a sunny day, and many of them will say 0, and a few of them will say 10% and so forth, because it's a very cloudy thing. So as a rough deal, we could say, well, suppose that we just took the mean of that group, and maybe there were 100 of those people, and took their mean, and said, well, that's a good estimate of where we are on the horizontal axis in this picture. And then we went to the vertical axis and we said what fraction of them gave each type of answer. And that should, and sort of under sort of, I think with this being reasonably exogenous, we should sort of see, does this thing trace out a pattern that looks like this? Oops. Did I lose my punchline? I surely did. Well, oh, there it is. Okay. Something happened in the copying process that shuffled these around. So this is sort of this is sort of the patterns you get, which really actually conform almost exactly to the pattern that we saw. That the upper left hand here, the fraction exact for young people. They're in the HRS. This was originally a set of people 51 to 61 years of age. More people gave exact answers. The older people aged 70 and up, were in so-called the head group. They gave fewer exact answers, but all of the patterns sort of followed this sort of inverted U shape, reaching a maximum at 0.50. The fraction that were 50, not 50-50, sort of went this way, and the zeros and the ones went that way. So that seemed to be some validation, at least suggesting it's worthwhile to go further. I don't know what's going on here. Huh. Well, let's see if I can get it to. Yeah, really shuffled these things. Okay, let me try again here. So kind of the answer, the idea of this likelihood function I'm now going to talk about, how to estimate this, is basically that you could look at the patterns of answers that people give who are in different groups, different risk groups basically, and with different sort of capabilities of giving precise answers, which may be related to their cognitive status. And we're sort of, here's sort of the center of these people here, and then there's this sort of distribution in the fraction of answers at each of those levels. Well, this is kind of a very inexact thing. Okay, well, I'm going to skip on. So here's the development of the index function. So we sort of parameterized this thing, and since I'm running a little short on time, I think I'm just going to skip past a lot of this, and we sort of develop a likelihood function. We divide the space into this kind of nonlinear region that's going to produce sort of one of my colleagues, Dan Hill, has done some programming that allows us to estimate a likelihood function over. This is basically, we measure the risk factors right to left and the uncertainty factors up and down. This is sort of this, again, this sort of bivariate normal distribution kind of thing that would give us fractions in each group. And this is the likelihood of an exact response looks like this, and likelihoods of 0. And now I want to move to the estimates. Okay, so here's the data that we're going to use. We're using data on people who are in the health and retirement study. They range in age from 51 to 90 years of age. Survival beliefs are assuming to depend on the knowledge of their own situation, ability to translate information into a probability, and we use a pretty parsimonious specification here, mainly to sort of see what we get out of this sort of thing. So in the view of time, I think I won't spend too much time here. I guess I'll just emphasize a couple of these things. One is that we use an optimism, what we call an optimism pessimism index. It turns out, sort of first noted in a paper by Robin Loewenstein, that people who give answers to the sunny day question, for example, tend to think other nice things are going to happen too. And indeed, what we find is if you do a factor analysis of the probability answers, there's a pretty strong optimism factor. It comes out that some people give more positive answers and some people give more negative answers. And so we use that in one of the models of this. We also notice that there's quite a bit of tendency to give focal answers, that these focal answers, people are giving 50s, 50s, and 100s, tend to give this, there's a tendency to give those answers across different questions. So we are interpreting this optimism-pessimism as essentially a kind of person-specific shifter in your survival beliefs. And we're interpreting the focal propensity as a sort of an indicator of the degree to which you have this kind of Knightian uncertainty. The model that we estimate is, the object that we're trying to estimate is this thing with beliefs. Here's the sort of survival index. You might want to, if that's readable up there, otherwise you might want to look in the table in the paper. We parameterize age with the Gompertz. I won't get into that. There's focal index. In order for identification, we can allow the U's to be correlated, but the Z's cannot overlap completely. So we estimate 3 different models. Model 1, demographics plus minimal identifying variables. Model 2, we add the index of optimism and is added to the survival index, and the focal propensity is added to the focal index. Model 3, we add subjective health status and health change from age 2000 to 2002. So we're starting to get into the actuary who's got his problems. With the exception of age and the focal index, the coefficient estimates are quite stable across the model. So I'm going to mostly talk about model 3. If you look at the demographics, mortality hazard rises with age, as it should. Males have lower survival expectations. Non-whites have higher survival expectations. This could be the truth. There's some evidence of racial crossover and mortality risk at older ages, but it could be optimism or denial that's associated with race. There's education positive effects on survival, but turns negative when health and optimism are held constant. And optimism, pessimism, the optimism index is highly significant. And a depression index of depressive symptoms is significantly negative. I wouldn't want to suggest a strong causal story there, because the bad health could make you depressed, or depressing could simply lead you to think things won't turn out so well. The determinants of the focal index, age has a positive effect, but it's wiped out completely when we put this focal propensity in. Education has strong negative effect. Cognitive measures are highly significant in both. Focal propensity is highly significant, and health effects are having worse than excellent and very good health in 2000-2002 is associated with an increase in uncertainty. How uncertain are the HRS respondents? Well, this is sort of, we can now go back and draw the estimated curves, because basically the coefficients in this model are really kind of these subjective distributions. So in the middle here, somebody who's got average beliefs and holding everything else constant. What is somebody has imprecise beliefs or precise beliefs using this focal index, so 1 standard deviation up or down. So, for example, the probability of survival at the mode goes from 65 in the middle to 71 if you have imprecise beliefs, to 62 if you have precise beliefs, and so forth. If you looked at the means, though, they're almost constant. So the increase in the focal propensity generates approximately a mean-preserving spread in the P's, in the distribution of P. If you look at the optimism-pessimism, 1 standard deviation change leads to a change in the modal response from 0.8 to 0.46, a change in the mean from 0.67 to 0.47. And health status and health shocks have effects, and I want to mainly go to the next point just to show that there's a calibration problem, and this kind of goes back. Suppose that this is in fact the mapping from a person's subjective probability beliefs from between answers and beliefs. And suppose we wanted to ask a bunch of people this question: how likely is it that you will live to age 10 years in advance? Okay, let's say that's the question. And you waited 10 years, and you said, how many of those people would have survived? Well, if you think about it for a moment, the right answer that you would like is the mean of this thing. That is, if people had exactly rational beliefs here, let's suppose for the moment that they do, then you'd expect, for instance, somebody who was in excellent and very good health that 58% of them would have survived by the next to the target. If they had very poor health, actually, if they had very poor health down in the bottom right, only 10% of them would, or excuse me, only 28% would be surviving. But the answer that we get from the survey, all of these things have unimodal, so they all are giving quote-unquote exact answers. But the answers they're giving are the modes, and we can see that the modes, when we start getting far away from 1/2, start to be really quite different than the means. So it would look like sort of their over-pessimism or over-confidence, depending on which way you go. That's where we are now. The conclusions, the model is intended to provide a mapping. It's trying to capture a gut response. We argue the mode is easier than the median. There's kind of a methodological question we discuss in the conclusion, is how can this modal response hypothesis be fast and frugal given the complexity of the mathematical manipulations to generate GFP, and we suggest a Friedman pool player defense. That is what we really are thinking is that there's sort of a pattern, and people are good at recognizing patterns. And the patterns that you get is sort of that something's really kind of precise, something's really kind of most of the time it won't happen. There's this lurking probability that something bad could happen, or God only knows, and that the circumstances that would lead people to feel that way are the things that we're attempting to model with this form. So we don't think the people literally work that way, but we also say the pool player is just a way station until we understand how the brain works. And there's actually now interesting work in neuroeconomics where you can look at people answer these questions. There's actually an interesting paper that was cited in a recent Science magazine article summarizing advances in neuroeconomics, which suggests that people who are presented with situations that generate ambiguity take longer to play a game than when they're not. And you have sort of contending systems according to this. Fast answers get answered in the middle of the brain, or in the emotional system, in the limbic system, and slow answers that require cognition get answered in the front of the brain. And you can see some evidence that sort of one or the other system is called on. And when people sort of get into an ambiguous situation, there tends to be a contest between those two parts of the brain about how to operate and think. So one could sort of take this line in that direction. And you've seen the other pictures often enough, so I think we'll stop there.
Okay, so I come from a very different field of decision under uncertainty, and I'll try to just comment on a few points of possible interaction between this work and what I happen to know a little about. So the first thing that this relates to in the recent literature on decision under uncertainty and the notion of Knightian uncertainty, one thing that sort of touches on this is a model of what we call the multiple prior, which means that, or tries to model a situation like this by saying if you don't know the probability, you entertain a bunch or a set of possible probabilities. This could be general measures on some measure space. And then the question is, what do you do with this? So one thing that comes out of a certain axiomatic derivation, that of course I will not get into, is that what people would do in a situation of decision, this is a little bit different because we're dealing with a decision and not just reporting probabilities, is to evaluate every possible act by the worst, the minimal expected payoff, expected utility payoff that it could give you, where the minimum is taken over all the possible probability measures that you entertain as possible. So this is roughly what this would look like. Since this model has been presented, there are many questions that have been asked about it, and in particular two seem to be quite prominent. First is why max mean. If you take this as really as a cognitively interpreted, the model is axiomatically derived from behavior, but if you take it as a cognitive interpretation thereof, it would seem like you have a bunch of expected utilities that could be associated with an act. Why go for the minimal one? It seems a bit extreme. The other problem with this, since the model is purely behavioral, is that it cannot distinguish between hard uncertainty in the sense that you have some hard evidence that tells you that there's a bunch of probabilities out there, and your subjective reaction to these notions. So this brought up an alternative approach. This is a paper that's very recent. It's actually not yet published, by Peter Klibanov, Massimo Marinacci, and Sujoy Mukherjee. What they suggest, and I think gets a little bit closer to the paper, is that when you have a set of probabilities, they also do an axiomatic derivation, which is some combination of behavioral and cognitive data. It's also in the context of decision. So they axiomatize a decision rule by which you look at a bunch of probabilities, but you also have a function that they denote by phi of sort of aggregating over expected utilities. So whereas the Bayesian would have a function phi, which is the identity or a linear function, and then the formula that you get here, well, the formula just looks, I'll just go over it quickly. You have the set of probabilities without loss of generality. You could assume it's the entire set because you have a probability measure mu over probability measures. So mu, take mu over the entire set of possible probabilities. For each probability P, you compute the expected utility. That's what we have inside the parentheses, say, on the left-hand side. And then you aggregate those, d mu, mu is being the probability measure over probability measures. But whereas the Bayesian would have an identity phi, which boils down to just iterative expectation, they suggest that this phi could be something else. And if you put there a function phi that's concave, you get to measure uncertainty aversion in a very similar way to the way you measure risk aversion. And one thing I liked about this paper is that it gives you, it's a very smooth model, as they call it, a smooth model, I think, in the title. Let me see if I have some advantages. Okay, so first of all, it behaves in a very smooth way. It's a more cognitively plausible than the max mean story that David Schmadler and I worked on, in the sense that if you really think of these as possible expected value, expected utilities, then you don't need to go necessarily to the worst case, to the most pessimistic one. And it allows one to distinguish between what is the things you really know in your mu and your subjective attitudes to uncertainty in your phi. Now, where are the links to what we see here? Well, the problems are a little bit different in the sense that all this is done in the context of actual decision-making, investing in a stock market where you don't have probabilities or something of that nature. And it's not clear exactly what people do when they're asked to give probability numbers. So I think that with the connection here is not entirely clear. But if I were to follow this line of research and say, okay, how would you summarize this GP? GP is basically what we have there. If I were to take a phi which is concave, trying to capture uncertainty aversion as in the Ellsberg example, then it's not clear that in your very bimodal distributions you would give 50. So, but again, this is very tentative because we don't really know what they have in mind or what problem they're solving, what they view as the payoffs of being right or wrong. But it's just not entirely automatic to me that the bimodal would be a 50. If these probabilities were probabilities they have to behave by or bet on, then maybe they should be a little bit more cautious and distinguish between the high P's for the good prize, which is survival, and the equally high G, the equally high density for the bed. Okay, the other question that's not clear to me, which is also related, is whether the 50-50s necessarily represents these very extreme bimodal ones. For instance, the uniform one, which you have somewhere in the middle, would seem to me like another candidate for someone who really knows nothing and has a completely uniform probability over the P's. Maybe that could also be something that could give rise to an answer of 50 on the questionnaire. So I don't know, these are just questions. Thank you. I'll give you some time for this one.
which I think relates both to your paper as well as some of the discussion on traffic. One possible, basically, if I understood right, maybe I misunderstood, but basically the distinction here between risk and uncertainty, the operational one, methodologically, is one in which there is one variance that is the variance across for a given probability distribution, and then there is another one which is the variance across probability distribution. Now, isn't that equivalent, if you sort of compound the two things, it boils down, after you compound it, to basically a probability distribution on the elementary events. So if that is correct, if this presumption is correct, then what is the difference then, between risk and uncertainty?
Okay.
So that's this is something.
Maybe
This is a question about the methodology.
Okay, so
Professor Shishinsky.
People having a spread, you ask people what is the probability at an age, a certain age, of surviving to a certain other age. More generally, you could ask people about their possible mortality table, function. In other words, what's your probability of surviving to time X and then Y, and so forth. Basically, the whole function, how very deep. One interpretation of the spread is that people are ignorant and they don't know much about it, and therefore you find the spread. There, I think you could look, and I don't know whether this has been done by anybody. As you go forward, people receive information. They know better about the risk class that pertains to them. And therefore, I would expect the spread between people to shrink as you advance in age. In other words, if you ask 50 years old, 35 years old, what is their mortality table, I expect to find a wide spread. When you ask 50-year-old people, what is their future mortality table, you'll find a much narrower spread, because I think in the meantime, information about their relevant risk class has arrived to people who know better where they belong. That's one interpretation. Another question I have about is the implication, pursue that for a minute. People who are optimistic, for example, more than the market, more than what you see. In fact, you would expect them to purchase annuities, basically, because these are people who can beat the market. They know something about it. They think they know something about themselves. And on the contrary, people who are pessimistic, you would expect to buy life insurance, because they think their probability of survival is less than what the insurance firms think they have. And my question is, has anybody looked whether there's a correlation between optimism, pessimism, and behavior? And finally, I'm asking you, have you looked whether firms are erring systematically? I think I know that I've seen studies that firms are on the whole fairly correct. Insurance firms, those who sell annuities and life insurance, are not biased, know pretty well. The money's worth is pretty good. Is that true?
The last question, Professor Candel.
I have a suggestion, because you're trying to identify the uncertainty. And the uncertainty, it seems like if you ask at the end of the survey, if you ask a question presenting the person with some piece of information of some precision, and then asking them whether they've changed their mind, the degree to which they changed their mind from their initial estimate to the information that you provide them would indicate the degree of uncertainty, because it's sort of like an estimation risk. I mean, they're not sure how to estimate the parameters. And if you give them, actually, you don't even have to give them the true information. You can just give them something sufficiently different from what they said. It seems like a way to estimate it independently of what they say, because you're essentially using their one answer to estimate two things. This allows you to separate.
Okay. Actually, let me take them in order. Alex's first question was well, there's sort of a probability distribution on probability distributions. Why do we care about this uncertainty? And indeed, if you sort of follow the expected utility model, that's where probabilities enter linearly into the objective function. You don't, and that's actually one of the beauties of the standard model. So if that's the way, if that's the object that people are working with, that seems fine. Now, Itzhak Goboa raised, there's a literature to which he's made important contributions about sort of non-expected utilities that one would deal with. But even if you stayed within the standard subjective utility, then whenever you're in a situation where there's sort of going to be subjected to repeated risks, and I guess life is like that, the thing that you tend to be ignorant about is something that you're ignorant about over many periods. A very simple example says, suppose that you're ignorant about the probability of draw out of an urn. If you knew that urn 1 had a probability of 1/2, and you're going to have to make 2 draws and you get a payoff of $1 for each draw, the distribution of payoffs is 1/2 or 1/4 chance that you're going to get $2, 1/2 that you're going to get $1, and 0 that you're going to get, or 1/4 that you're going to get 0. If you had, say, a uniform distribution, then the probabilities of each of those payoffs would be 1/3, 1/3, 1/3. The payoff distribution for the second urn would be riskier than for the first urn, for the completely standard reasons. But the source of the risk, and basically the source of the risk is because p squared is a nonlinear function of p, and so on. So there are a lot of situations, particularly ones that are in these kind of dynamic things where the uncertainty is about some process, like what's my mortality rate, where these higher moments are going to matter. Let me go to Eitan. Let's see. So he talked about, ignorance versus... Could you restate? I wrote something down that I now don't know. You asked me a first question, and I wrote down something about ignorance. Oh, yeah. This is actually something that we've got very interested in this paper. I didn't emphasize it here, but there are kind of two different things. Say, let me make the contrary case, and then maybe later we could talk about how to figure out what, because I accept what you said as a quite sensible thing to have said. The contrary case would be, I'm the representative actuary. I know all of the data. And I think of myself as being well represented by millions of people in the denominator and other millions of people in the numerator that give a mortality rate. So in the sense of uncertainty about the mortality rate, I have very little uncertainty. What starts to create, right? My probability of, I can go to the life table and I can compute my probability of 0.63. And I'm sure that's the right probability because I think that evidence is all relevant to me. Now as hold on for a second. But as we go forward, what starts to happen to me are things in which there's no sort of frequentist evidence available. So when I get this strange cough, is this a serious thing or is this not a serious thing? And so in that sense, as health events start unraveling, you can actually have situations in which you learn more about your health state and you revise the mean downward, but the spread part also tends to go. Now, optimism, pessimism, does it relate to behavior? Yeah, it's actually very strongly related to behavior. And indeed, this precision, this riskiness argument that I was making, people who are more uncertain in the sense of this focal index, both these cases, people who are more optimistic tend to buy more stocks, they tend to hold riskier portfolios, they tend to have higher wealth, holding a bunch of other things constant. People who have higher propensity to give focal answers tend to have less risky portfolios, have less wealth, buy fewer stocks. Let's see, on insurance, I don't know. That's a good topic. And then in terms of the suggestion, I'd like to hear more details. So we actually, in the HRS, one of the things that we've done is we have a set of what we call experimental modules at the end of each wave that are about three minutes worth of questions. So the timing is about right from what you said. And we use those questions to try to address sort of interesting hypotheses, and we put some on. So if there's a good experimental module, we actually have a deadline in about 6 weeks for getting drafts of those and deciding which ones we're going to do. So.
Thank you very much. I'm sure that this bigger discussion may be carried later on. And now it's Yoram Ruffle's turn. It's going to talk about
everybody here is using extensions, so if you do the question as well.
Well, then there's a mapping question. What's the mapping from beliefs to yeah, see, because give an answer to seconds. How does that?
Smoking. So, over time, more about your otherwise, I may be.
With Gary Becker from the University of Chicago, and obviously, if you don't like something, you have to blame me, and if you like it, you should say something to Becker. Okay. So, what is this paper about? In this project, we aim at explaining within the framework of rational choice models why low probability events, such as the likelihood to be harmed by terror, affects people's behavior so much. We put forward a theory incorporating into the expected utility theory situations in which the extreme consequences associated with consumption of risky goods and the extent this turns into a silent phenomenon affects person's mental state, generates fear, and by that affects people's utility and well-being. Using data from the US and from Israel, we provide empirical evidence to support our model. We identify the effect of fear, and we calibrate risk and fear aversion parameters which feed the data. So I would like to start by apologizing that I will have to switch between softwares, and I hope it won't be too brutal and it will be worth that. So I'm doing it now. Okay. So this project started 2 years ago, in the summer of 2002, while I was visiting Chicago. More or less 1 year after the tragic events of September 11, 2001. And I met with Becker, and we asked the question whether we can explain, using rational models, what seems to be as a very large effect of terror on people's behavior. And for example, here you have data on the number of tourists that are arriving to Israel by year and month. So these numbers are a little bit high relative to the average before, but you can see the numbers during the end of 2000. And this is the date in which Sharon visits to Al-Aqsa. And then the huge drop in the numbers, something at the magnitude of 2/3 and even more. Okay? And you can see some of the known events. The suicide bombing outside the disco in Tel Aviv, the Sabao stuff in Jerusalem, and quite recently, the second Gulf War. If you look at the data these days, it's more or less here. Maybe part of it because of this conference. So, and the question was whether we can explain that using the statistical value of life models. So here you have a simple calculation, which I did. Which I think demonstrates that it will be hard to fit this data with the standard expected utility model and the value of statistical life models. So I took the number, the worst month during the last 3 years of Intifada in terms of Israeli casualties. And the number was 130, which is 4 times more than the average per month during this period. And so what I'm doing in this table, I'm calculating by how much a one week visit to Israel, what is the cost of terror in terms of for a guy who comes to visit Israel for 1 week, in terms of the expected loss, in terms of his value of statistical value of life. So I take the number of 130 divided by 5 million. Let's say we take the Arab population out of this calculation, or the Jewish who are living out of the territories. So this is the probability to be harmed during a week. I take from Aschenfelter and Greenstone the upper bound of the value of statistical life as estimated in the US, which is far above the average for, let's say, the typical tourist to Israel. And the cost is about $10, which is, if you are a guy who pay $500 a ticket and live with your family here or with friends, it's 2 percentage points. So it will be hard to fit the tourism data to this change in the cost of visiting Israel for 1 week. So, so let me move back. And indeed, in some sense, at this point, we didn't have a reasonable answer for the question. Better was sure the data is wrong. Or it will behave okay later. And I didn't have any answer for that. And as you can see from the motivation, we were not the only one to raise this question. It is especially after September 11. And it's not surprising that understanding the causes and the consequences of terrorism, and especially in its current form, is a challenge that economists find hard to resist. And there were 2 questions that people pay the most the attention was on 2 main questions. First, trying to understand why some young, educated people commit suicide. And the other type of question was trying to estimate the causal effect of terror on aggregate outcomes, and there is a paper by Eckstein and Sidon on that. However, this paper ignores an important question, which is why terrorism generates such large influence on people's behavior. And the large aggregate effects were often attributed to some ignorance. So there is people ignorance. And most of the paper use the Tversky and Kalman prospect theory to justify this ignorance. And I thought that in some sense it can be interesting to try to fit it using the differences between risk and uncertainty as presented by Hansen and Sargent, in which you don't know exactly from which ball or the shocks are being pulled. And the perceived, and the popular argument was, as you can find in Action and Sidon, that the perceived impact on the probability to die might be larger than the actual one, which is quite fair. We didn't have a large effect of low probability events. It's not something limited to terror. we can say something similar to that when it comes to issues. For example, you have examples as the mad cow disease, the SARS epidemic, which it looks like people overreact to that. And the question is whether we have a good explanation to that in a simple or not simple, in a rational, using a rational choice model. And I told you I didn't have any reasonable story for that. So here, in some sense, my wife helped me. And it was around, I think September, yes, it was the same day, September 11, 2002. The Sears Tower in Chicago came with an offer to visit the observatory for free. And my wife told me, look, Yona, we should go. It's for free and things like that. Let's take the kids. I was a little bit disappointed because I'm an economist. She knows that I'm an economist. Economists, especially labor economists, we know that time is money. It's not only whether we pay the ticket. And therefore, I decided not to go into arguments with her, and we prefer to go there, save time, maybe it would be less expensive. So we went to the Sears Tower, and here I'm moving again. So this is really the beautiful Sears Tower in Chicago, and you can go and check in the data. September 11, 2002 was a beautiful day in terms of weather. We went during the evening, and it was actually empty. It took us 1 minute to find a parking lot outside without paying, no lines. And we found ourselves upstairs on the observatory with very few people with us. Okay? So about, I think, less than 10 people. And, you know, I already knew the view. So I pay more attention to the people than to the view. And I realized that what people are doing is trying to watch what are these lights outside. Are there a type of lights of a plane? And if it is a plane, what is exactly the direction of this plane? And eventually, everybody found themselves downstairs very happy, and the mission was accomplished. And this was at that time, I realized that maybe I'm not a theorist, maybe I'm not using the correct terminology, that the story is a little bit different than the standard expected utility model. In the sense that in the standard expected utility model, even in the state-dependent versions, there is an uncertainty when people take the decisions, however consumption being taking place after the uncertainty was resolved. So you make a decision, and then it's either the good state or the bad state, and then you consume. However, in this type of situations, actually we consume when the uncertainty is not resolved. And this affects the utility that we obtain from the particular consumption or activity within each state of nature. And so we can think about other examples. In other words, to take it to the mad cow disease story, I say that beef is not so tasty when you think that maybe there is something there, and the fact that you learn weeks later that you were not contaminated by the disease doesn't bring you the pleasure. And it's even more so in the case of unsafe sex during the time of AIDS. Okay? So if you meet somebody, and let's assume there is some utility from being with new partners, the fact that you will learn weeks later that you are okay and you are not contaminated won't bring you the pleasure back. Some of the pleasure that you lost because of that. Okay. So this is one element of the model of the story. That the fact that we consume when there is still uncertainty about the state of nature depreciates the utility under risky activity, even if we survive. And therefore, the risk affects not only by changing by imposing some cost in terms of loss of expected value of life, but also in terms of losing utility. However, it's not as simple as that. Obviously, with Becker in the team, we could not avoid the investment story. And what is the investment story? The story is the following. Look, fears, it's not a story which is limited to terror. We have fears in many aspects of our life. Even for me to stay here, it's not fearless. So people face fear, and they can handle that. They can handle that by making some investment. Investment is not a free lunch. They have to pay for that. And therefore, and more than that, it doesn't pay the same to everybody. So those who will find it, profitable, will invest and overcome fear. And others will substitute to other type of activities. So this is the story that we have. So to summarize that in words is that in the end of the day, the fact that there is some risk to life affects our decisions or affects have two channels, the risk channel and the fear channel. So there are previous papers that dealt with that. The paper by Akerlof and Dickens, in which they have the cognitive dissonance. In this paper, people they convince themselves that it's not so dangerous as the true probabilities suggest. Elias and Spiegler show that it's not so trivial to model that. And Kaplan and Lee, they talked about anxiety and fear. However, in their paper, in their model, people cannot, they do not allow people to invest in order. And so in this aspect, it's very different. So the model is a very simple model. I will go over the model briefly, and then I will go to the data. So it's a two-period model, two goods, risky good and riskless good. Consumption plans determine the probability to survive, and the probabilities are common knowledge. Agents maximize their expected utility. The probability to survive is only a function of consumption of the risky good, and declines in a constant hazard rate. As with respect to fear, fear is a function of two parameters and decisions that people take. Gamma is the hazard rate, I already discussed that. S is the extent in which the risk is a silent phenomenon, whether we talk about it or not, whether can we avoid it from when we watch the news and things like that. So there is another element besides the pure probability to survive. And M is the investment that people make, are allowed to make in order to overcome this fear. So S and gamma affect positively F, and M is something which reduces it. So the utility function, we assume that it's additive and separable over goods and time. The F is good dependent in the sense that it depreciates the utility from the risky good and only from the risky good. Okay, this is the budget constraint. We assume perfect capital market and full insurance system and perfect insurance system. And so this is the budget constraint. They can invest and consume, and we normalize the price of investment to be 1. So agents solve this problem. They maximize expected utility subject to their budget constraint. And what do we get from that? So I would like to emphasize maybe one or a couple of results and then go to the data. The first one, I think, can be illustrate using the marginal rate of substitution between C1 and C2, the risky and the riskless good. So as you can see, we have three terms here. What each one of them tell us? It tells us the following. Look, this is the marginal rate of substitution in economy with no fear at all. So we have no risk, S is equal to 0, gamma is equal to 0, and this is the standard marginal rate of substitution. Now we have two additional terms. This term is the risk effect. What is the risk effect? It's gamma times consumer surplus for consumption of the optimal bundle, and in addition to that, the fear effect. Note that if people invest and invest enough, and I will come to that, F may be 1, and in this case, this term turns to be 0. So you can see that we have an additional term which affects people's decisions, which is above and beyond the direct effect of this gamma on the marginal rate of substitution. So we have four main results. This M, investment and consumption of the risky good are complementary goods. Investment increase with A, which is the taste to preferences toward consumption of C1, decreases with risk. And the most important one in some sense is that for any S, gamma, and M such that F equal to 1, F equal to 1 is the case that we have no risk, there is an A bar such that for all A that are greater than A bar, F is equal to 1, and for all others, F is greater than 1. So people can, so there are some people, and especially if gamma is not very high, will make the investment and will overcome risk fear totally. Okay. Okay. So maybe I can show that using these simple figures to be sure that everyone is with me here. And here the figures are for the case in which, for a particular version of the model in which the investment is a kind of a, there is only one program which eliminates fears, or you either take it or you don't take it. Okay? So this is, okay, this is strange, okay. Okay. This is the utility before we had any fear or risk in the economy as a function of C1 over C2. And obviously, this is the point in which we maximize expected utility, and therefore, this is the optimal consumption band. When we introduce risk as a result of that fear into the economy, the expected utility as a function of C1 over C2, the slope goes down. And it is because that fear depreciates the utility from C1. And therefore, without investment, we move to this point, with having lower levels of C1 relative to C2. So we substitute from C1 to C2. If we are allowed to consume, to invest, and this is the investment cost in the case in which you have only one program, who are the people who will choose to invest? The people who will choose to invest are those that will find their expected utility to be higher with investment than without investment. And these are the guys who consume a lot of C1, relatively speaking, before the shock. Okay, those who consume little from C1 will find it not profitable to invest. The expected utility is higher without investment than with investment, and they will choose not to invest. Okay. So what can I take from that in terms of summarizing the point of the model? The higher the consumption from the risky good, it pays more to invest and overcome fear, and C1 lovers will even invest more than others. However, there is another point, which is important. And if we may borrow Adam Smith's phrase, the extra effect of risk via the fear channel is limited by the extent of economic incentive to overcome fear. And this goes back to the paper by Kaplan and Lee. So we cannot justify everything by fear. Saying, okay, people there is a point in which it pays back enough to invest, overcome it, and limit it, and put a limit to the effect that fear may have, or potentially fear may have. So people who had previously consumed large quantity of what turned to be risky good will invest, overcome fear, and practically keep their consumption plans unchanged, and others will substitute to the risky activity by other consumption plans. Okay? So we have a model in which the same exogenous shock will generate two different effects on two different types of persons, that we can in some sense identify them given the consumption they had before the shock. Okay? So with this intuition, we go to the data and we are aiming at doing two things. One, identifying the effect of terror via the fear channel on the consumption of people. And the other thing, to calibrate risk and fear aversion parameters for a particular utility function. We are going to do it by comparing the outcomes of those we project to be investors with the outcomes of those we project to be non-investors. Okay. So the treatment effect will be estimated using standard differences in differences estimator. If this is the outcome of those who do not invest, and this is the risk effect, and this is the fear effect, T is the level of terror in our case. These are the outcomes of those who choose to invest. They are only affected by risk. Taking differences in differences, we get a D. As with respect to the structural model, we can do the following. Let's take the constant relative risk aversion utility function. Okay, in the version or in the that is well known and often used in the macro literature, and add this F parameter into the utility function, multiply basically the consumption, the utility from consumption of the risky good. If we do that and we model the fear of person using the following switching functional form, for the case in which we have one program of investment, it's either you invest and overcome fear or you don't invest. So DI is equal 1 if you invest, and equal 0 if you don't invest, and this is the fear people have if they don't invest. Then, substituting this into the first order conditions and taking logs, we receive two outcome equations. This is the consumption of the risky good for those who choose not to invest. Okay? And this is the consumption from the risky good of those who choose to invest. Assuming that the consumer surplus is the same for both type of agents, okay, conditional on their observed earnings, and assuming that prices do not change over time, then the differences in differences estimator actually give us the parameters of interest. It gives us the theta over alpha, and theta is the fear aversion parameter, when alpha is the risk, the standard risk aversion parameter. So eventually we will be able to say something about this. Okay. So now I will move to the data. Not everything that I will show is something that identifies the effect that I was talking about. Some of the things are just kind of supportive evidence. So if you think that something is not good is not identifying my point, you are absolutely right. So I will bring one piece of evidence from the US into this presentation. You have more in the paper. What you have here, it's a kind of an index in which we have air passengers relative to air freight ratios. Okay? In the US, we start in, I think, 98, and we end in March 2003. You can see that this index was practically flat before September 11, 2001, and it's still substantially below after September 11, 2001, and we use the freight in order to, in some sense, control for economic activity. And this shows that it's significant. So this is the only piece of evidence that I will bring from the US in this presentation, but we have more evidence, and you can find them in the paper, about the outcomes of pilots in the US in terms of wages and employment. And the evidence we have show a substantial decline in the wages of pilots without any change in the likelihood to be working, suggesting that it's a kind of a demand side story, okay? And it's not that, we don't see any evidence that pilots are asking for extra compensation. We cannot rule it, but we don't see evidence for that. We are going to identify these parameters using the Israeli data. And before moving to the Israeli data, let me show you some statistics about the incidents in Israel, casualties and type of incidents. So the blue line shows the number of casualties per month in Israel from the beginning of the last wave of violence till the last time that I updated the data. And you can see that it was about 20 fatalities, okay? 20 people died on average per month. And this March 2002 was really an outlier, and we know that, okay, in some sense. The yellow columns show the number of suicide bomber attacks that were taken not on a bus, where the red columns show the number of suicide bomber attacks that were carried out on buses. And we are going to use this variation in order to identify. So you can see that it didn't start, or it started only 1 year after okay, so it's around 2001, beginning of 2001, that at least in this wave of violence, suicide bomber attacks were carried out on buses. From the aggregate data, and let me show you some aggregate data on the number of bus passengers, we find the following. We regress it against different, we regress the number of bus passengers against different type of terror incidents. Okay? So in the first column, the number minus 0.191 means that the number of bus passengers declined by 20% approximately when we, in a month in which we have a suicide bomber attack, which was a suicide bomber attack that was carried out on a bus. To be sure that it's not a kind of a spurious correlation and things like that, we regress that against all other type of incidents, and you can see that the only thing which actually, in some sense, is correlated and quote-unquote explains the number of passengers is the number of suicide bomber events on buses only during this month. So it's not as crazy as we might have think. So now I'm moving to the micro data we have from the expenditure surveys, the Israeli expenditure surveys. We can get, if we ask, the consumption of people by a very fine resolution. Okay? So what I mean by that, we can see how much money they spend in using the buses, public buses, in usual routes and not in usual routes, in daily tickets or monthly tickets, and I will use that. The amount of money they spend in coffee shops and things like that. And in addition to that, we have their personal characteristic that people often use in order to control for other possible explanations. So in this table, what we can see is that, again, we regress. So each table will have two versions. One version to show you that we control for other variables, and the other version in which I will focus on the important numbers. Okay? So here you can see that we find in the micro data more or less the same coefficients as we found in the aggregate data. And the number minus 0.31 means that in a month in which we had a suicide bomber attack carried out on a bus, the number of bus passengers in the public routes declined by 30%. We divide that into big cities and small locations, and the reason for that was that terror actually took place in big cities, and you can see that the effect is only in the big cities and not in the small locations. Okay. Now, this is not enough to identify. What we did in order to identify, we did the following. We took advantage of the data that we have. This is the Ruffle is here. Contributed to that. So we said, look, let's, in order to distinguish between those who use or have more incentive to consume, to invest than others, let's look at the consumption of those who use it on a monthly basis in relative to those who use it on daily basis. And as you can see, the effect is only on the consumption of daily tickets. Those who consume it on a monthly basis are not affected at all. You may come and say, look, perhaps it's an income effect. To be sure that it's not an income effect, we replicate this exercise, repeat this exercise for different levels of income, and we find that the effect is basically only on those with the daily tickets and is not sensitive to people's income. Okay? Now what we did, we look for other type of consumption, which is the consumption in restaurants and coffee shops.
So how do you know that the guys who bought the tickets actually went on the bus?
I don't know, but I know that he's buying the
ticket.
Buying
Already bought it.
But maybe the coffee shop will help me to answer this question, because here you pay basically not in advance. Okay? So we thought that another thing that we can use in order to identify these parameters is the consumption in coffee shops. What I want to show you in this table is that the consumption in coffee shops is not affected at all from suicide bomber attacks that are carried out on a bus. However, they are affected from the number of fatalities, and they are also affected from the suicide bomber attacks that were carried not on a bus. In order to identify our story, we said, let's take people that we expect them to be heavy consumers of coffee shops and pubs and restaurants. These are the single people. And compare that consumption to the married guys. However, the married guys have, some of them, or most of them have kids. So in order to keep it as close as possible to a treatment and control group, we took the married guy without children. And as you can see here, singles are not affected at all. They continue to go to coffee shop, and here they pay after they get the coffee. And while married people are affected a lot. Okay?
Except for Loewenstein, so we all went to a serious car, women and children included.
Okay, so now so these are the kind of treatment effects, and if you believe that these two different type of groups, as we classify them by monthly user, daily user, or singles versus married without children, is one type being the investors and the other being the guys who switch to the riskless activity, we were able to identify the effect of fear, of terror via the fear channel, the treatment effect of terror via the fear channel. Now let's move to something a little bit more ambitious, and which is to estimate this risk, say something about this risk and the fear aversion parameter. At this point, we can do more using the prices of the public bus transportation, in order to re-identify both alpha and theta. But here, what I'm doing is the following exercise. I'm asking the following question. For each level of risk aversion parameter, tell me what is the fear aversion parameter which fits the data. In this particular constant relative risk aversion utility function. So what do we get here? If we believe that a suicide bomber attack that is being carried on a bus reduces the utility from taking this bus by 15 percentage points, which is less than a quarter in terms of money, then the risk aversion parameter that we need in order to fit the data is at the magnitude of 1. A very conservative risk aversion parameter. And in fact, you can see that the range of risk aversion that we need in order to fit the data using reasonable, if I may say, fear aversion parameters, it's quite conservative. It's in between 1 to 4.
What do you mean by 15% how much money it's worth to me?
Relative, yes. Yes. What is the change in the price has to be? Exactly. Now, another thing that is important to notice here is that the higher is the risk aversion parameter, the smaller is the fear aversion that I need in order to fit the data. And this is not surprising. This comes back to the point of coupling and being. In some sense, fear is an issue only when it's not, risk is not an issue. Okay, when risk is a big issue, when risk is high, I don't need fear. Fear is not relevant in explaining our behavior. Fear is relevant in explaining our behavior only in the cases where the risk is not very high. Okay, and this is in some sense different from the alternative explanations that I mentioned before. So I don't know, I think that I have to end by that. So let me conclude by saying, and maybe I will refer later to some other points following your questions, that in some sense, okay, what we find here is a support to our story that, there is fear there, however, we can invest and overcome it, and that it depends a lot on the economic incentives to who are those who are going to invest and overcome it, and who are those who are going to substitute with different activity. Another point that I want to show before going to the last slide that I have is it's data that it's from regression that I didn't run. Okay, so this one you can trust. Okay. So it's data from the mad cow disease. It's basically from a paper by Ada, who actually used the mad cow disease and the French data to tell a story. I will tell you what is the story that he told. Basically, he argued, and I think he provides evidence to support that, the crisis, the mad cow disease became a public, known to the public in France about 1 year after actually the disease actually spread into France. So using panel data about the consumption of people, he had them data about how much beef they consume before and after. He was saying, his theory was the following. He said, look, since it was 1 year after the epidemic spread, his model said, or his basic argument was that those who consume a lot of beef were already sure that they were contaminated, and therefore they continue to consume beef, while the others thought that they have some chance to escape that, and therefore they substitute to other type of meat. And he provides the following coefficients. He was saying, look, before the crisis, basically people did not switch the elasticities with respect from beef to better quality meat were actually 0. However, after the crisis or during the crisis, you find that people that used to consume low levels of beef switch to other type of meat. However, those who consume a lot of beef continue to consume. So if we take our story to his data, I think that we find some support to our story in his data. So to summarize, in some sense with respect to this terror issue, we may say that in some sense terror take advantage of people being human and rational. By generating fear, terror, even in the form of low probability event, may generate substantial effects. And in some sense, what terror does, it generates large-scale effect by damaging the quality of our life rather than affecting the quantities of our life. So it doesn't affect really the probability of survival, but the quality of our life. So thank you very much. And
thank you, Professor Sidon.
Mouse is impossible. Okay. Let me start by doing a brief pre-introduction on the topic, some background, and then I'll make especially 2 points about the paper. I'll try to be brief, so we'll be on time. One thing that surprised me for a long time is that economics paid basically no attention to the issue of defense, security, etc. While even in other countries, not to talk about this country, defense spendings are high and perhaps higher than money spent on crime deterrence. Very little economic analysis is available on the topic. The economic analysis that was available on the topic was mostly falling under what Professor Lucas defined a long time ago, development economics. Is basically things that we don't know balanced against things that we don't understand. And that's like crowding out versus other type of externalities of expenditure. This is where the science of defense economics was, I think, back 5 years ago. Practically no attention in the literature was paid to the fact that defense expenditures, or what we try, or what we achieve, or what we don't achieve, bring some security, and that this security may do something to economic activity. Perhaps the only justification I can think of was that we thought that, if on the balance against military spending stand these huge wars that cause a lot of damage, and therefore it goes without saying to say that we are fighting this damage, and that's all. Nothing else needs to be said. Actually, I'm not sure this was exactly the point. Most of the wars in the second half of the 20th century were not large wars, were done elsewhere for most people, and the effect was not very large on some of the combating economies. I can also say that at some point in the mid-90s, I sent a paper about this topic to a journal, and I got 2 remarks about the paper. One of them was right. One was that the paper is bad. The other one was that there are no more wars and the issue is uninteresting. So the paper was bad, by the way. So, but I think that people paid no attention, and given the fact that people paid no attention, it came as a major surprise that once people start to analyze mostly after September 11. Some of us started to think about it before in this country. People got into a big surprise that we got tremendous or large effect of small events. Okay, basically, terrorism didn't hit too much of the economy anywhere, and the numbers that we got when we tried to estimate were too large, even for the people that estimated them. Okay, Abadi came with very little terrorism in Spain, in the Basque region. He got numbers of about 10% effect on the economy. It depends, different numbers, but it goes to 10%. Tzvika and myself got about the same type of numbers for much higher level of terrorism in Israel, but still not something that can be explained. And then I think that the real puzzle is that after not doing any economics of security or insecurity or defense, or every person can choose the politically correct word he likes, after not doing that for many years, we were extremely surprised by the facts. And the fact is that terror has a huge impact on economic activity, or at least is correlated with a drop in economic activity. Okay, whether it's a causal or not, I'm not sure we have found a right answer. Terror was defined as a low-intensity conflict by people in other fields. And as I said, the direct effect is small, and after you play with these models and you manipulate and you try this and you try that and you push the model back and forth, I think the basic point that where I start where I agree completely with Yona is the fact that we will not find an expected value story that will make sense to us. Okay, you have to play with this model. There are different, there are hundreds of alternatives. I guess I tried 10 out of these hundreds to get the feeling that you don't get the right numbers for such models, and you are all invited to try the other few hundreds of possible expected utility stories. So we are looking for a new story to explain the effect of terror on individual economic activity. And what Becker and Rubinstein proposed is indeed a novel story. And I think Yona explained it fairly well, so I have very little to add. But the general idea is that we are being affected while we consume, and not by the fear, and not by the fact that we think, or by the fear, and not by the fact that we may end this consumption too early by being blown up. Okay, this is the one leg of the explanation. Terror, by the way, if you look at the dictionary and not in the CIA dictionary, which is what economists usually do, just go to regular dictionary, it's precisely that. It's terror, right? This is the way a regular English dictionary will define the terror as a fear, as something that is in the individual, as something that you impose on the individual, and it's not the CIA definition. I think it's a reasonable one. It's a better one than the CIA. The other thing that exists in this model is that individuals can invest to become, in some way, a Yona type, superhuman. They're not scared anymore. They have to pay some money for that, but they can do that. And given that, given that it costs money, they will do that if it pays. And this is the general idea. People are afraid, which I think is a very reasonable statement. They are afraid. This causes them to, of course, this fear is attached to goods that make them more exposed to terrorism. So if I am at home, I'm less exposed. If I'm in the coffee shop, I'm more exposed. And then the second step is that if it really affects me, too much, I can take a step against it. Now, the first question is, does this formulation make sense? And to me, it makes a lot of sense. Being a non-single, but those who know me know that I like coffee shops, especially in Tel Aviv, not so much in Jerusalem. It's too costly in terms of life expectancy, but in Tel Aviv, at that time you would go to a coffee shop in Tel Aviv. There's at least one economist that went with me to a coffee shop in Tel Aviv at that time. At every moment somebody would show up into the coffee shop, all the eyes would be at him. Right? People would sit in a coffee shop, and once a person would step in, everybody would look at him. So I guess this is another, this is not exactly, this is eye econometrics, but it's true eye econometrics. I think that everybody was around actually understand what I'm saying, and therefore I think the story makes a lot of sense. Is it the only story around? I don't think the story should be in conflict with other stories like Kaplan and Lee. They fit some situation, this fits other situations, and there is no reason to try to say, this is something that this is correct and this is incorrect. There are many cases where our feelings are unimportant for our economic choices. There are some cases that are. Some cases would go Kaplan-Lee way. Other cases, like Fehr, I think would go more in the direction that Yona is providing. Now, what I have against this statement is something very minor, but it's more about the focus of the paper and not about what is in the paper. And that's the question, to what extent this view really explains the magnifying effect. Okay, the goal that we have in our one of the goals that we have in our mind is to explain why small probabilities have such a large effect. Now, what happens in this paper is that these small probabilities are taken further away from our eyes. In what sense? When we talk about expected value, probabilities, estimating probabilities, miscalculating probabilities, we understand what it is. And then we say, when we misperceive the probability of 1/10 of 1,000 to be of 1% multiplied by, thousands, this is a big misperception. However, when we take this same event and we bring it into the Fehr function, then we don't realize what we are really saying. What we are really saying is exactly the same. It's a functional forms that transform this, and you put it in the theta and data, but I think that we're still very far away from understanding to what extent the fact that we moved this probability from being outside the utility, like in the expected utility sense or in the misperception sense, to move it into the Fehr. Why are we so afraid? Right? Let's ask ourselves the question. Why are we so afraid from an event that never happens? I mean, none of us, even all the coffee lovers in Tel Aviv, none of us have gone, thousands of times to a coffee shop. During this period, we all work, to some extent. So still, this effect is very small. I think here we are still, the model did not tell us enough, and there's a little bit of a veil, and this question remains open. And my kind of feeling that at the end of the day, we will have several stories that will add up together. Okay. I will jump over, Yona summarized very nicely the fact that he documents, so I will jump over that, and I want to say one more thing about that. All these facts fit the model, and as Yona said, they do not identify the model, but they fit the model. The question is it the only story that they could fit? And this is, since this is a conference for Yoram Weiss, I think that, everybody, if I just show you the list of results, people that drive buses all the time, drive buses. bus drivers that drive buses, they take the loss on themselves. Another explanation will be a lock-in effect. Something I'm saying Yoram Weiss because those of you who know his literature on SS know that this is basically a lock-in effect. So a lot of this behavior can be explained by lock-in. People that drive buses every day are people that have very low elasticities or really cannot change, or people that consume coffee can form this habit and cannot change or switch away from this habit. It is another explanation. What we need for the story of Yonah to be identified, we need something about the investment. We need to know that these people indeed, some people in some data, take an actual investment to forego the fear, or we can try to identify it in a different way. But there is no simple way to do that. All in all, I think the story is very interesting. For me, it's new. I don't know, I'm not an expert on non-expected utility papers. I think it makes a lot of sense. I think the data support this, with the caveat that it doesn't really support this magnifying effect. And I think that there is still a lot before I'm fully convinced that this is what the story behind the data.
Okay, Yoram. Okay. Maybe we'll take one question.
No?
Yeah.
Okay. Just to pick up on your point, I was thinking of another story that maybe could fit the data. Basically, of course, what you provide is a real probability that you have been, you're going to be victim of a bomb attack, which is very, very low. But of course, there's also the subjective probability, your own probability to be attacked, that could be totally different than this one. And then we can provide maybe a social interaction model, in the sense your own probability will depend which type of person you will interact with. So if you're a single guy and you go to a cafe, obviously you will interact with people that are very exposed to this kind of bomb attack. And because of that, you will have this social multiplier effect, and then your own probability will be totally different with the real one. And this discrepancy can explain this kind of behavior. There's a paper by Sa in the GPE about crime behavior, and they want to explain why people commit more crime. And because some guys who live in some neighborhoods, and there's a few cops coming in, the subjective probability to be arrested is totally lower than the other one. That's one of them.
Okay, that's the last question.
I have three brief remarks or comments. First, I mean, that's exactly Danny's point, but I agree that you don't give evidence of an investment. I mean, I certainly understand that there is heterogeneity in behavior, but I don't see why it should be investment instead of just people at different tastes. The second thing, okay, the puzzle is why is it that people overreact to very small probability events? I don't mind calling that fear, but then the question is, how is it that some type of events generate a huge fear, whereas other types of events were even more likely to happen don't? For instance, you're alluding to the mad cow disease. It had a huge impact on behavior of French people. Now, the probability of being killed by eating cheese, raw milk cheese, and being killed by listeriosis is about 50 times as high, and there is no fear linked to that. So it seems to me that really the heart of the matter is why is it that in some cases we do get some fear, in some cases we don't. I think all the action is getting there. I mean, then you can say that fear decreases with thought. And exactly on this point, maybe at least for some of these events, one explanation could be the difference between risk and uncertainty. The example you gave of the Sears Tower at the beginning, it's typically a situation of uncertainty in the sense that the probability that precisely on that day, on September 11, 2002, there will be a terrorist attack on the Sears Tower. I have no idea what it could be, and it could have been large in principle. And it's the same with the mad cow. I mean, one of the driving forces in the mad cow is we know that the impact. We know now that the impact was small, but by that time there was a worst case scenario in which hundreds of thousands of people would be infected. So if you think it like in Boas-Meidler of the multi-Krayos model, that's how you explain it.
Okay, so thank you very much for comments. I will be brief. Danny said that I'm not scared, I am. And actually, about the model, I think that one of the results in the model is that we are not going to invest in order to avoid fear that is generated from something very risky. It will be extremely expensive to overcome this fear. So actually, our model projects that we will find very little people that are going to the Sears Tower or to the Empire State Building and they think about jumping and then they say, look, I will overcome the fear and jump. It's not about that. According to our models, we will find it not possible to invest unless there's few crazy, but it's not about the crazy guys. Whether we identify or not, given the assumptions that I gave, we identify, okay? If you believe that our classification of these consumers into investors and not investors, you believe in that, then we identify our story. And it goes to, I think, your question, identifies the parameter of interest. I'm going to your question about subjective probabilities and things like that, or people sitting in coffee shops and then they learn that it's actually not so risky. So let me tell you that one of the reasons that we choose terror in Israel is that, as at least the Israelis know, in Israel there are no secrets. Okay, so information is common. Okay, especially with respect to terror. It's not that there was some kind of information in particular coffee shop. Look, actually, it's not so dangerous. It's worth taking the bus and let's take this arbitrage. Basically, people, I think this is an example in which, if we can think about the examples in which information is quite common. As with respect to the taste, and I think that's a good one. In order to rule out the taste story, we need indeed the consumption. What do I mean by that? As Danny pointed out, we have also evidence about bus drivers, whether they continue to work or not. With respect to bus drivers or pilots and things like that, since we believe that there is a kind of specific human capital they have, it will be too expensive for them to move out, and this is the lock-in effect that you were mentioning. But with respect to consumption, it's more easy to believe that people are adding margin. So there are differences in taste that will be reflected in different elasticities of response, but all of them have to end up consuming less. However, we find in our data, and Enda finds in his data, that those who consume a lot before that do not switch. So here the identification indeed comes from the fact that the group that we classified as investor do not reduce their consumption at all of the risk. So,
okay, let me thank Yoram and Dan Zidon, and I wish also to thank Yoram again. I know Yoram for exactly 2 high years, question whether we would have also another conference on the 3rd high. For that would need both women's estimation. So let me wish you now well, and now we'll go for a coffee. Thank you.
Well, we will try the best.
Just some motivation, some literature review, and the way the game is set up, the way we solve it, and what kind of policy we can address. We call it the key player policy. And at the end of the day, we can also show you that we can apply our problem to terrorist networks, and how, for example, what we call the key player, which person you have to get rid of in order to destroy as much as you can the networks. And well, I'll be more clear on that, and I prefer, since I have 45 minutes, to get in the model directly. Just in terms of motivation, as I say, is basically to get here. Okay. Here. Okay. What we think is crucial here is that depending on your position in a network. And we want to have general results. So any network you can think of, you can have star-shaped network, you can have complete network, and so forth. We give you example. Depending on your position in the networks, then the welfare effect will be very different. So what we think here is when you think of peer effect, instead of thinking the way we usually think as a mean approach, we want to think as a distribution approach. So we want to introduce heterogeneity here. And basically, there's a lot of application that you can think of on our framework. The first one, which Calvo, Armagon, and Matt Jackson have done already, it's application to the labor market. Obviously, when you look for a jobs, well, your networks matter very much in getting your jobs. Another paper that I've been thinking of is public goods, the contribution to public goods. This is a paper by Bramoulet and Rachel Crampton, where they try to understand free riding problems in a network setting. And you have also other type of application. For example, you have R&D, research and development. How much you're going to invest depends obviously on the network structure you are dealing with. There's a paper by Goyal and Mora in the Rand. And of course, what we focus here in crime decision. And there's a lot of evidence, especially in sociology and criminology, that crime behavior are strongly influenced by their peers and by their networks. So I don't want to get into all the literature, the empirical literature, but there's a lot of literature showing that. Just to show you what kind of literature we're dealing with, there's one literature which is I think quite well known now. It's about network formation. And the key paper is obviously the Jackson-Walensky paper. And then there's some other paper in different fields. You have another field which we are using also. It is more in physics and sociology. All this paper on the right-hand side, that's published in physics literature, where they use this kind of approach. And you see the way we want to bridge the two approaches. And then there's some paper about crime, of course, Gary Becker, but you have also Sutherland and Haney, who are coming from sociology and criminology, showing this importance of peer effects there. So, I don't want to spend time on that, but there's a lot of empirical results, both in sociology and more recently in economics, showing that peer effects do matter very much in crime. I just give you some well-known papers. Case and Katz, most of them try to use natural experiments to try to capture these effects. Of course, a paper by Glaser and Sassadon and Scheikman, which is also well known, they try to show that you take different areas with the same fundamentals, and you have huge variation in crime. And what they argue is that social interaction is one explanation, and they try to estimate. That was Giorgio was showing this morning with this covariance stuff. And you have this paper in the quarterly by these guys using the moving to opportunity program, showing that also if you move people from poor area to less poor areas, then the crime rates will drop, and so forth. So you have a lot of paper in this literature, and showing that indeed you have important interaction effect in crime. Now, just to summarize what I say, you have these two effects, and both in sociology and in economics. Okay, so now, sorry, some of the slides, I don't have the paper version, so I guess it's not as good, but I hope everybody can read this. Okay, so what about peer effect? So where do we stand about peer effect? And that's the first thing I want to bring that. We know, of course, there's a lot of influence of peer effect, and most of model of peer effect just predict average dependence. And of course, what we want to show you here is that actually what matters more is not the average effect, but it's a distributional effect. And the way we will capture that is through the position in the networks and how this heterogeneity will affect behavior here. So, and this is to summarize what we are doing. So what we do basically is we try to keep track of all the bilateral influence in the group. So if I'm interacting with someone, he's also interacting with other people, so to see the way that works, and this is the networks. And then of course, we want to have a kind of geometry of the network, so who is who in the network, who is the important guy in the network. Some people are important, influential, some people are not. Who are these guys? How can we identify with some kind of measure? And the last thing, of course, is, well, if you want to apply some policy about that, who is the guy you want to get rid of? So if you take a terrorist networks, is it Osama bin Laden you want to get rid of, or is it another guys? And obviously, the way we do that is not, the answer to the question is not trivial here. Okay, so I want to start, because we will use a kind of linear quadratic utility function, so go back to the discussion of this morning, I want to show you that it can capture a class of problems. So let's start with a standard problem of networks, of peer effect. So think of a standard peer effect problem. So you have each agent just to have to choose some level of effort in anything. For example, in a crime, how much effort you want to put in crime. In public good, how much you want to contribute to the public good. In R&D, and so forth and so forth. So this is utility function. What is crucial here, obviously, is the cross-derivating. In other words, the influence of your peers on yourself. Okay? So the cross-derivating is crucial. And the only thing that we assume and that we need here is that it is constant. Okay? So I call it sigma ij. So this is a way that, in general, you do that. Now, what we do, just a bit more, just to have more general issue here, we use both strategic substitutes and strategic complementarity. What does it mean? It means that the other, if the other do something, the more they do something, the more we do that. That is complementarity. But you have also other effect when you have substitutability. Because we want to have a general framework, we use these two concepts, and obviously you have particular case when you don't have this kind of thing. So in terms of notation, what I assume is that the minimum of these effects are negative, which is substitutability, and the maximum is positive. So you have complementarity. So we don't want to have the two effects here. And the condition behind is very close to Alberto's condition. You want to guarantee that you want to have a unique equilibrium, so you want to have global substitutability at the end. Okay? And so what is important now is that if you are in this structure, which is a standard network structure, then what is crucial is this slide, is that basically you have a matrix on all these cross effects. Okay? So the diagonal, you have your own effects, the sigma ii, and on the off diagonal, you have the cross effects. So this is the matrix of bilateral influences. What we can do is you can decompose this matrix in three parts. The first part is only the idiosyncratic concave effect, so the sigma ii. The second part is what we call the global substitutability. So all the effect that the more people do something, the less you will do it. And then the last thing is the local complementarity. Now what is new here is that you have this matrix here, which you don't have in the standard peer effect, which is J, which is an agency matrix. And I will be very clear about that. This matrix describes the networks. Any network in the world, you can have a matrix that corresponds to that. And I will give more precision about that. This is a matrix which gives you all direct links between people. And I will come back to that, okay? So what we do here, because we can decompose this matrix in these three parts, okay? Basically, and this is the crucial argument now, is that you can get this utility function is consistent with this decomposition of this matrix. So basically, this utility function, what you see here, which is a linear quadratic utility function, is consistent with all the model of peer effect that you have in mind. And what you see is that you have two parts. The first part is my own effect on myself. So when I put effort, I have this concave, which is the first part. The second part, you have two parts. You have the gamma and the lambda. The gamma is what we call the global substitutability. Okay, the global is not the people in the networks. People are, okay. And the last part is the local complementarity. Okay? So what I mean that all the results we will present today will be valid for any function that has this structure here. And this is quite general in the sense that it captures this type of model of Peer effect. As long as you assume that the cross derivatives are constant, and then you need to have some condition of that guarantees that you have unique equilibria. So the global subtlety effect that I just put before that. Okay. So now I want to apply this type of framework to a crime issue, but all the results we get, you can get for other issues. So if you think, for example, of R&D, so you have the firms who have exactly the utility function, and then you have this effect of substitutability and complementarity, and then you can model that. Of course, if you want only to have complementarity, like for example Jorg this morning, then you put gamma equal to 0, and then you get this result here. So now, how we feed, how we model this crime decision game. So we use exactly the same function that I just proposed now, and there is different way you can put the network here. And after reading all this literature in sociology, we felt that the more convenient way is to put in the cost function. So you have two effects here. You have global subtlety and you have local complementarity. What does it mean in this crime framework? It means that, well, on the proceed of the crime, there is congestion effect. Okay, so more people are criminal, the less you're going to get in terms of booty. Now, on the cost networks, on the cost, you have the local complementarity. What does it mean? Well, the more people you know who are criminal, okay, the lower is the probability to be caught. Okay, why? Well, because you have a lot of story in criminology, for example, because this is what we call the know-how. So because these people, they learn you how to do crime, you are more effective, or they tell you, well, you can go there, and maybe you will be more efficient, and so forth. Another way to interpret the model is just to assume that the cost function is the time you spend in prison. So the more you are friends who are criminals, the lower will be your digit in prison. That's another way to interpret this type of model. Okay? So just to repeat what I say, what is crucial here, the gamma is what I call the global substitutability, and the pi and the lambda stuff is the local complementarity. Okay? And what you want is that globally you have substitutability. Otherwise, you get to this complementarity games. Okay. So now I want to solve the problems. Okay. So the first, so I just write again my utility function as the one I chose before, and you get exactly what I say. You have the private effect, the local effect, and the global effect now. Okay. Now the key question here, if you stop here, you say, oh, this is only a Peer effect model. What I want to show you here, what is crucial is what we put in the local complementary effect. In other words, what does it mean, this GIG? What does it exactly mean? Okay, that's where the network is coming up. Okay. And this is where we use graph theory for this purpose. And this is where we are here. Okay. Now, what is crucial here is I just say, if I have a link with someone, okay, I call it GIJ. And this is what we call undirected graph. If I have a link with someone, he has a link with me. Obviously, in this framework, it makes sense. And it's equal to 1. If I don't have a link, it's equal to 0. What is crucial, again, it is the agency matrix. So how does it work? You see, I just take a very simple graph with 3 players, and it's a star-shaped graph. Why? Because player 1 is a star, he has 2 links, and all the other one have 1 link. So what I can do, I can represent exactly these network structures in the matrix form. As you can see, player 1 has no link with himself, he has 1 link with player 2, and 1 link with player 3. So this is the first line, 0, 1, 1, and so forth. Everybody see that, okay? Now, what is crucial, which is, again, a result from graph theory, what is crucial is that this agency matrix has very nice properties, one of which is the following. Now, if I take J over square, what does it take? It gives you all the links of length 2 of each player. What does it mean? Well, see again, player 1, it has 2 links of length 2 with himself and no links of length 2 with the other one. How can we see that? Well, take player 1, And of course, if he go to 2 and come back to himself, that's the length 2, he has 1. And if he go to 3 and come back to himself, he has also 1. Okay? And more generally, this adjacency matrix, and this will be crucial here, have a nice property that G over K counts all the links of length K of each player. And this is very crucial in this paper, will be the key aspect here. Okay. So now, given we have that, basically, we solve, the following game, one of the properties of the matrix obviously is symmetric and it's a 0, 1. We solve the game for pure strategy Nash equilibrium. And what do we get when we solve the game? This is what we get. Okay, so if you solve this matrix, we can show that, of course, the equilibrium exists and is unique. And there's some conditions which are not very binding here. And so the form of the Nash equilibrium of this matrix form here. But, and then you have some comparative statics, which is quite obvious. When you have more dense networks, you have more crime. Why? Because of local complementarity. That's nothing. Now, what is crucial is for us is the next result, okay? Okay. What we discover is that there is a huge literature in physics and sociology try to identify in any networks who is a more central player or whatever you are considering with. Okay? And there's different measure of centrality. One of them, you just take the number of friends. So the guy who has the most direct links is the one with the most central pair. Then you have other measure, closeness between us and stuff like that. And I give you the way it works. So one of the measures that they're being putting on is the connectivity measure. What do? You keep track of everything. So I keep track of the length 1 links, length 2, length 3, length 4, and so forth. And I put different weight to that. Another one say, well, between us, no, we only take optimal paths. For example, the shortest path. So if you take the example behind that, if you take the between us measure, then you will never go, if you go from 1 to 3, you will never go through 2. Whereas if you take the connectivity measure, you go through 4. What we're going to show you now, because this is a big debate, so you have maybe 30 measures of societies. And these people argue which one we can take, they don't know. What we're going to show you now is that our Nash equilibrium corresponds to exactly a very well-known measure in sociology. So basically what we give you here is behavior foundation of some centrality measure, and which is quite intuitive for economists, I guess. And I want to define it now. I want to show you the Nash equilibrium, okay. So one of the measures, which is the first one, we take all the possible paths in the networks, it's called, it's the following one. Okay, it's called the Bonassi measure. So Bonassi, this guy in 87, defined a measure, which is the one above, which is the beta above. How does it work? Well, what you can see here, what you basically do, it's a sum of phi k, gk. And what does it mean? You take all the links of everybody, of all the links, but you decay less and less. Phi is less than 1. So you put a high weight to direct links, you put a low weight to lengths of 2, and so forth and so forth. Okay? And that's what we call the Bonassi measure. So that's the way he says the more central guys is the one with the highest Bonassi, is the one with the highest Bonassi measure. And what I'm going to show you here now is that our Nash equilibrium in terms of F for crime is exactly this Bonassi measure. So this is a, sorry, yeah? Oh, no. Phi, it's, yes, it's exogenous. It's a ratio between the lambda and gamma, so subtlety over complementarity. So it's parameters here. Okay? Okay, sorry, one thing I didn't say before. In order to be able to write, this matrix form as a sum, affine sum, you need one condition on the phi. It has to be less than 1 over the largest eigenvalue of the matrix G, obviously. And this is the standard. Okay, so what you find, the first proposition, I think we were surprised because we didn't expect that. Well, what we find is when you calculate the Nash equilibrium in effort, EI star, it's exactly proportional to your Bonassi measure. In other words, if I take any networks, any form network you want, I can define in terms of Bonassi. Why is it important? Well, first, you know who is the most central player in the game, but you reduce the problem of the networks. You know, when you start with the network problem, you have n minus 1 links to solve, because that's the complete networks. But now you have only n data to know now. So you switch from n minus 1 problems to n problems. So you really reduce the problem, the dimension of the problem. So any of the problems we have this peer effect kind of forms, you just give directly the Bonassi measure and you get exactly who is going to commit more crime, who is going to put more R&D effort, who is going to put more public good, and so forth. Okay? So what I say, you can rank people according to their Bonassi measure directly. So, and of course, once again, that's what we say from the beginning, the crime outcome or any effort outcome in peer effect vary with location. So what matters here is that if you are friends with someone, it depends on his location on the networks. So if you are friends with someone who is not very central, it doesn't matter very much. But if you are friends with someone who is extremely central in the networks, in other words, he has a high Bonassi, then this will strongly affect your behavior. So if you do R&D, for example, and you want to decide how much R&D you put with a friend, depending on his position network, you don't put the same effort in R&D. So this is what is crucial here. So compared to a peer effect, obviously, the structure of the networks will change. So if I do application now, I take different structure of networks, like I take the star-shaped networks or the complete network. I will have totally different result, obviously, here. So once again, if we go back to this idea of peer effect, okay, as I say, the standard peer effect it's really the idea of being homogeneous across group members. Here, obviously, this is totally different. And once again, you can decompose the two effects. The E star, it is exactly the peer effect, the standard one. And the one on the left, this is the network effect. So, for example, now we try to estimate this type of model, then you don't have the reflection problem here if you estimate this type of model, because you have exactly the contribution of each of them. If you know the Bonassi measure, you can solve this kind of problem. Okay. So, I will speak about empirical test afterward, but okay. Now, of course, if you believe in this model, if you believe that networks are important in crime or in any type of this situation, then obviously the policy you can address is not the same. In the standard Becker model, you say just punish everybody the same way. Now, you cannot do that anymore. Now, people are different in the networks. So, as we say here, in the standard model, you just shift the distribution. You just punish everybody the same way. Now, obviously here, we cannot do that. What we want to do now is that who is the person you want to get rid of in these networks so that he will damage as much as possible the networks. So, and what you show here, what we will show here is not only the guy with the most criminal. It's not the one with the highest Bonassi measure. Why? Because there is two effects. The first effect, of course, when you get rid of this one, you get rid of this criminality. But one is away, you still have a network there. And you have to see the indirect effect on this guy who are staying in the networks. And that's why make the things a bit interesting. So, this is what we call the key player. Okay? And once again, what the solution we will give you will be, again, a geometric solution. So by solving the planar problem, we give you a new centrality measure. Not the Bonassi, but a new one, obviously, that solves these problems. And the one we propose one is what we call this intense centrality measure. I will give you the formula there. It has two things. It has these betweenness ideas, that you have to take count of everybody, but it has also to include the contribution to other centralities. So it's not only that you are central yourself, but how much you make the other central to the networks. And this indirect effect can show you that the key player is not always the Bonassi guy. So basically, this is the problem I want to solve. Okay, just G minus I is a network without the key player. And as I said, there is two problems. So the planar problem is to maximize this difference. And of course, it's equivalent to minimize the Bonassi when you get rid of the key player. So if you solve this problem, you can define a new measure, which we call an optimal measure, because this is not a market, obviously. And this is what is here, as you can see. Theta I is our new measure of centrality, which is a measure of the key player. And what does it take? It takes two things. First, you have beta I, which is a standard Bonassi measure, which takes only the direct effect. But then you have beta gi, which takes the indirect effect. Beta gi is how much you contribute to the others. And basically, if you think of the matrix G, it's off the diagonal. Everything which is off the diagonal of the Peer effect here. And what we show here is that the proposition is that the key player is the one with the highest intercentrality measure here. And just maybe to give you more intuition about that.
Clarifying question, what's the definition of a key player?
Oh, okay. The key player, so when you have a networks, in this kind of crime networks, who is the player you want to remove so that it has the highest effect on crime, total crime levels? Okay, so exactly. Okay.
So follow up on this. You had this optimization problem.
Yeah.
Maximize the E.
Yes.
Yes.
No. E is a total level of crime in the economy. E is a sum of all the effort of each person.
You want to minimize the difference, not to maximize it. Something in the definition that
Sure. Yes. Yeah. So E star is the level of crime in the economy when you don't get rid of the guy, and E star afterward is a crime level when you get rid of the key player. So that's what you do. You want to reduce. Yeah, that's what you do. You want to reduce the level of crime afterward. Yeah.
Before you do, let me ask you a question. Is it obvious that if I reduce, not key players, but if I reduce the players, is it obvious that the crime must drop?
Yeah, of course. Yes. Yeah, because I show that. Yes, I show that in the comparative statics result of the Nash equilibrium. Okay. Exactly. That's exactly from local complementarity. Yes.
What is driving that result? Because if you think about an environment, for example, you could imagine that one of the criminals is, you could think of that as a monopolist, whose effect on other people is such that think of a criminal who controls crime, and the optimal level of crime is less than if you take out that monopolist and then the rest of the criminals.
But yeah, that's not this model. This model.
What is the assumption in the model that's avoiding that?
This model is people commit crime alone, but they have friends who are criminals. So when you commit crime, you don't engage people. You're not a monopoly in crime. So you just commit crime by yourself. We don't deal with gangs. I think you have in that a guy with.
Thinking of external, maybe I don't. I'm the only criminal. And I do my crime.
Yes.
And I also tell anybody else that if they enter the neighborhood, I kill them. So that way I keep the level of crime. I control all the crime in the neighborhood. It's not a question of gangs. It's just that my externality, my effect on the others is I get rid of them. So what is the assumption? I'm trying to understand what assumption in the payoff is ruling out the externality effect.
Okay.
The payoff model.
The payoff model is like that. When I commit crime, there is two effects. Okay. The more criminal you have in the economy, the lower is my proceeding for the crime. Okay. But the more people I'm connected with, in terms of crime, the lower is my probability to be caught. So I reduce the cost function here. Why? Because I will. There is some technology. That's all. Okay. Or you can have, another model that can give you that, but this is it. Okay, so of course, just one more thing. If just to go back to this idea, if you compare what is the difference between Bonassi and the intercentrality measures, the key player measure, what you see here is that theta I, once again, is the intercentrality measure, the one of the key players. And what you see here is that you can write it as beta I over this mii over beta I. Okay? And mii is just self-loop. In other words, how many links that start from yourself and come back to yourself. And the more you have self-loops, the lower is the center state measures, and the more the bonus is important, obviously. So what's happened here, the key player become different from the bonusy is when you have more and more indirect friends and so forth. That play a big role here. That's what will affect here. And just to give you, let me give you an example. That's okay? Okay, let me give you an example which just gives you the solution here. Take this graph. So as I say, I can take any graph. I take this graph because you have a nice structure here. What you see is that player 1 obviously has a key, is a bridge guy, but he has only 4 links. Whereas the criminal of type 2, 6, 7, 11, they're not bridge guy, but they have 5 links. Okay. So when you start with a small phi, okay, what you see is that I calculate 2 things. E star, beta, and theta. What does it mean? E star is how much crime you're going to commit. Beta is the bonusy measure of yourself, and theta is if you are the key player or not. Okay? What you see when phi is small enough, the key player is player of type 2, the most criminal. But when you increase phi, the key player is not anymore the most criminal guys, which means the guy of type 2, but it becomes type 1. Why of that? Well, as I said, the key stuff of the key player is that the indirect effects are crucial here. When phi increases, you put more weight of the lengths 2, 3, 4, and 5. So obviously what's happened, the key player now is the one who contributes more and more to the other centrality measures. And 1 is crucial there. Okay? Just to show you that the key player is not always the one with the most criminal in the networks there.
Question for you. Yeah, sorry. Did you say that this is, you're assuming some symmetry here?
No. Symmetry from where? There's no symmetry. No, there's no symmetry. People are identical ex ante, but they're not identical in terms of position in the networks. So, for example, if you compare 2 and 3, they're not the same. Okay. 2 have 5 links and 3 have 3 links. Yeah. Okay, so there's no symmetry in the model at all. We solve for the general case.
Well, yeah, there is not one bit position.
Yeah, but people are totally identical, only the position is different. Okay, what means that they're symmetric there. Now, of course, how much time? You've been tough here. Okay, just one thing, of course, is it worse to do a key player policy or like a type of Becker policy, like just punish everybody the same way? What we show is that, of course, it depends how much heterogeneous are the workers. If you take a complete graph, everybody identical, doesn't matter very much, it's the same policy. But the more people are differentiating the networks, the more it's efficient to do the key player because it will harm much more than that. Now, what we do also, just to, so this is this formula, I'll just give you what I just said, is that this is a variance of the measure over the mean. And what you see here is the higher is the variance. When variance is equal to 0, eta is a type of Becker policy, the equivalence. The higher the variance, obviously, the more efficient is this policy. So what we do in the paper, maybe I will not present here, is that we generalize to the group player. And the generalization is not also trivial. In other words, what do you do if you want to get rid of, let's say, 5, 10, any finite number of people at the same time? And what we, sorry?
Variance of what? The variance is the variance of what variance?
Sorry, I don't get it.
Variance.
The variance of the thetas. Theta is the eta-centrality measures. So how much the vary is about that, okay? Now, what we do after the group player, and what we show, actually, you cannot do the group player like you do the key player. In other words, what you can do, you get rid of the first guy, and then the second guy. That doesn't work. So the measure we define a new measure. I will not give you that. I will just give you the example, like before, of the group player. And imagine now, imagine now, it's the same case like before, and the key player was player 1. Imagine that you want to get rid of 2 at the same times. As you can see, the one you have to do is 2 and 7, or any like that. But if you get rid of 1, it's not efficient. So if you do sequentially, it will not work in this case. If you do 1 and then 2, that's what you should do, then it doesn't work here. So we define a new measure that how many a finite number of people you want to get rid, and you have a new measure of centrality measure. Okay? And at the end, we try to endogenize partially the networks. I'm just finishing. Okay. And basically, what we do is say, imagine that you do another things. There's a first stage decision where you decide to be in the labor market or not. So the first stage, you decide to work or to be criminal. And second stage, if you're criminal, how much effort you want to put in crime. Well, what we show then, taking the same networks, then you have complementary policies. So you can have policy of wage and crime at the same time. So here you do two things. You can increase the wage, for example, and you can increase also, you can do the key player. And what you see, obviously, the guy you got to get rid depends on the level of wage. Why? Because of the dropout effect that you have in the first stage. Okay? And so just one slide, and then I'm finished. So basically, what we say is that if you take any peer effect that have our structures, anyone you think that has a structure, then you have the relevant measure to understand that is the Bonassi centrality measure. Any peer effect that have this kind of structures, that's the first thing. And of course, then you can address policy. If you are in a crime frameworks, okay, you get rid of someone because that's the one you have to do. But what we're doing also is to say, imagine now you have this kind of peer effect, but now you have R&D collaboration. You don't want to get rid of the films. You want to subsidize. So the question you can to say, for example, can we apply this framework to which firm, for example, in Europe, should we subsidize in the networks? And of course, we can answer with the same way, defining a new measure of centrality measure. Okay, so this framework does not apply only to get rid of someone, but you can subsidize someone, and then, you don't believe me, Ethan, but this is really the one. This is the last one. This is okay. When I say before, one of the crucial aspects here is that we reduce the dimensionality of the problem. When you do network, you have a problem of dimensionality here, because when you start with the networks, you have n players, and if you take the complete networks, each of them n-1 links. So you have to deal with the problem of n-1. And here what we say, well, the problem is only n-dimensional. What you need to know is only the Bonassi, and you solve any problem you want here. Thank you. Pedro. I hope not too long. You were with a stick. So maybe I should sit here.
Just a few comments. Basically, the only kind of comment that I have about this paper is trying to simplify it in a way and trying to see if you can get new questions coming out of the simplification. So essentially the paper, I think it would be easiest to say that the paper is about strategic choice of some activity level, it doesn't have to be crime as Yves said, when there are negative global externalities and local positive externalities, where the local externalities, the question of who exerts a positive externality on whom, depends on the network features. So everything is given by the network. The local externalities are given by the network. The simplest possible version of the model would be given by this thing. So every player in this game is going to have to choose his effort, E. And player I's utility function is going to be given by this formula. I put this A in order to make sure that the model will have a positive solution and everything. But essentially, you can see this is not an innocuous simplification of Yves' model, because if you actually look at this formula, it means that the phi measure that he had is equal to 1, and then he can't develop the Bonassi measure. He really had to assume that this phi was sufficiently small to get all the technical machinery working. So it's not an innocuous assumption. The story that I can tell about this thing, so let me switch to the next slide. Before telling a story about this, an alternative story about this model, let's then rephrase the question. The question is, who's the key player in this network, in the sense that if you remove, if you remove this player from the network, you will get the maximum possible reduction in the aggregate activity level in Nash equilibrium. Now, the inspiration for Yves' talk is coming from crime networks, but for me, sort of the easiest way to kind of relate to this paper was to think about organizational behavior. And my story was that you have some team, you have some organization, and you have a tendency to free ride your teammates' effort. But if you're linked to somebody, if you're his subordinate or maybe he's your subordinate, you feel a bit embarrassed free riding him, so you don't do that. So you become conscientious once you're linked to somebody else in the network. And so once I thought about organizational behavior, then this suggests to focus, for example, on particular networks, which is a tree graph, a hierarchy. Now, if you restrict attention to the hierarchy, then maybe, I conjecture, I haven't solved it, haven't tried to solve it, maybe you can solve Eve's a question, which is, in Eve's paper there were two measures actually. There was one measure, the Bonassi measure as he called it, which actually tells you what the level of activity is going to characterize each player in the network. It isn't a purely geometric measure because it's also depending on the parameters, the phi. But essentially, give me the Bonassi measure of each player, and I'm going to tell you how active he's going to be in equilibrium. That's one aspect. So in Eve's, according to Eve's interpretation, how much crime is he going to commit? What's the crime level that he's going to commit? Another measure, the intercentrality measure, told you who's the key player. Okay, the key player is the guy with the highest intercentrality measures, and his example towards the end of his talk illustrated that these two measures can be different. They don't have to coincide. Conjecture, in a hierarchy they do coincide. Now I don't know that, so, but let me then just state the question very simply. So you have a hierarchy. It's the simplest model of a hierarchy. You have two tiers in the hierarchy. There is one big boss. He has K immediate subordinates, the foreman, and each foreman has M direct subordinates. I call them workers. So it's a two-tier hierarchy. And in this simple model, you have two alternative. I think you have two alternative natural measures of centrality in a network. One is, as Eve said, the number of direct links that you have. And the other one, and this is related to the Bonassi measure, but here because phi is 1, it's actually the number, I'm sorry, it's related to the intercentrality measure. It's how many players become connected exclusively thanks to you. Okay? So you're sitting in a certain point in the network. Now the question is, if I take you out, how many players, how many pairs of players will become disconnected because of you? And I completely disregard the length of the path from one player to another. I just ask the question, how many players will become disconnected if I remove a player from the network? The nice thing here about this example is that the big boss, the guy who stands at the top of the hierarchy, is always going to be the central player according to the second measure. Whereas if K is larger than M, I'm sorry, if M is larger than K, then actually the foremen are the central agents in this hierarchy. So now the question is it going to be the case that the big boss, the guy who stands at the head of the hierarchy, is the key player? So the two questions, the two twin questions actually are, is the big boss, the guy who stands at the top of the hierarchy, is going to be the key player in the sense that if you remove him, you'll cause the maximum possible damage to the organization? And second, is he going to be the most active player in the hierarchy? Now, why do I present this simplification? Because, and this is my only, essentially my only criticism of the paper, I think in the sense the paper is too general. It might be quite worthwhile to simplify it in two dimensions. One is remove a few parameters. I agree this will completely change the technical features of the paper because the technical features of the paper depend on this phi being sufficiently small, so you need these many parameters, but maybe it's going to be beneficial to remove a few parameters, and second, to try to focus on certain natural network types that we see in reality, for example, hierarchies, and maybe conjecture in a hierarchy there's going to be an equivalence between one type of centrality and the other type of centrality. In particular, the big boss is going to be both the most active player in the hierarchy and the guy whose removal is going to make the maximum possible damage to the organization. It's a conjecture. I think it's worth pursuing. That's all I have. One other point. Of course, the model is very general in the sense that the applicability is huge. You can think about I/O applicability not just in the sense of R&D, but also thinking about merchandising. So, for example, suppose that initially, before you have Disney, you have manufacturers of dolls, T-shirts, bunch of toys. Once you add Disney into the picture, each one of these merchandise, these commodities become connected to Disney in the sense that there are local complementarities between the two. And now the question is, if you remove Disney out of the industry, how much damage is it going to create to the other firms in the network? So it might be interesting to investigate these things in a traditional I/O setting. That's all. Thanks.
Thank you.
I want to follow up on Ronnie's point about thinking of this in terms of organizational theory. There's a large literature thinking about different kinds of organizations. Sometimes they're called command organizations versus interactive, or centralized versus decentralized. And the idea there is that if you have a centralized organization, everybody's talking to one guy. So there's a foreman who talks to all the subordinates. And if you pull out the foreman, you lose a lot. Whereas if it's an interactive organization and each person is talking to a lot of other people, if you pull one out, you don't lose very many. You don't lose very much.
Sure.
So think about two kinds of crime organizations. One is a very centralized crime organization, and one is kind of a decentralized one. If I'm the cops, I want to go after the centralized ones because it's a lot more efficient in terms of use of resources to pull one guy out of that. So then, defense for that, of course, is for these families to try to decentralize. And if I extend that, think about that in the context of the firm, again, sort of picking up on Ronnie's idea, what that suggests is that when I think about firms, one of the reasons that they go to flat structures rather than these very hierarchical structures is because they're worried about the vulnerability associated with losing one guy, or either through hold up or other kinds of exogenous factors. So I think these things are all very closely linked to this organizational theory, and probably be helpful to bring some of those ideas.
There were some papers, prestigious ones, horizontal ones.
Yeah, that's it.
Any other more questions? Chuck?
Yeah, a few things. First, if you're really applying this to crime, the assumption that the police have full information about the structure of this is problematic. With an organization, maybe that's a good assumption, but with crime, maybe not. Second, there's no notion of the cost of pulling out the key figure. One in a way that a crime organization might try to protect itself is by hiding who's the key player. So I guess that's related. But furthermore, why don't these organizations try to reconstitute themselves? You've assumed that the relationships are fixed. Why you can't elect a new head? I mean, you think you?
Yes. Okay. First thing. First is well, it's rare that when you do a very general model, they say you should be a particular case. In general, it's the contrary. So okay. So one thing, what I'm worried when phi equal 1. Okay, there's two things. First, you cannot have bonassi, and the second thing also, I'm not sure you get uniqueness. You may have because you need to have local you need to have that cross derivative of the function have to be negative at the end. And phi equal 1, I'm not sure because you are I think that you are exactly as the case when you are in between the two. So that's one thing, and that's my complication. Of course, we can do application. Basically, as I said, we discovered afterward when we wrote this paper that there was published paper in the RAND and different journals that have done exactly a particular case of what we were doing. There's a paper by in the RAND R&D networks by Goyal and Mora. What they're doing, they do exactly what we're doing, but they cannot solve the problem. So what they do, they just do particular cases. They say, let's take a star networks, or let's say complete network and solve it, but we cannot solve for the general case. What we think is important here is that we have a complete characterization of the class of equilibria we have here. And that's important because you can solve for any networks you want. As long as, well, the only condition on phi have to be less than 1 over the largest eigenvalue of the adjacency matrix. Why? This gives you two things. This gives you the fact that you can write a Nash equilibrium as a Bonassi measure because of the cycle, but also guarantee that all the value of effort are positive. Otherwise, they may be negative. That's two things that give you, so that's important. Now, full information about networks, I didn't present the slide here, but there's a lot of things, a lot of paper, actually, that can show you in real world, they can have exactly the information on all the networks. And you have also socioeconometrics research on networks showing you that you need to know 20%, 30% of the people to reconstruct the networks. So this is not easy as in an organization, but still you can have a fairly good information about the way the network is structured and the way it works. The last question you asked me basically is all this, what about endogenous networks? Okay, obviously. So when I proposed the last slide about participation in the labor market, in some sense, you were endogenous network because when you do the key player, some people will drop out in the networks, and this will have this effect that the network will differ. Now, if you want to endogenous the networks with like Jackson-Walensky type of approach, let's say pairwise stability, you can solve Nash equilibrium, but the problem is too complicated for the key player. You need to have some, you can maybe do with computation, but this is very, very, because now you have three effects. You have the effect that when you get rid of someone, how much you damage himself, the other one, and how people will reconstruct the network afterward. And that's a very hard question. Okay.
Thank you.
Thank you very much.
We're moving to the second and last paper of this session. Rather than capo di capi, it's about people who live in the fast lane, I guess. Divorce, remarriage, and child support. And the author that we see, the author.
The younger guy.